The first thing that feels wrong about the cosmos is not its size, nor its darkness, nor even its silence. It's the temperature of its intention. Stand long enough inside the thought of the universe, and a strange realization begins to form. Its rules are not shaped for life. They do not favor it. They do not welcome it. They tolerate it only in a narrow strip of possibility, thin as dust drifting through a beam of light. Life appears not because the universe is generous, but because a few parameters stumbled into balance before collapsing toward the abyss again. A balance so fragile, a single decimal place shifted up or down, and no star would ignite. No atom would stabilize. No chemistry would last long enough to dream. And still, we exist here, inhaling the cold mathematics of reality, as if it ever wanted us. There's a feeling subtle at first, that the universe behaves less like a cradle and more like a filter. Not a place where life naturally arises, but a place where life accidentally slips through. The early universe was a white-hot flash of energy, hostile to complexity. Hydrogen formed only because expansion and cooling arrived at the exact pace required. If expansion had been slightly faster, atoms would have torn apart, slightly slower, and everything would have collapsed into a singular ocean of fire. And yet, out of that brutal infancy, came the thin possibility that something as delicate as carbon-based metabolism could emerge. If you ever sensed a quiet indifference in the night sky, you were not mistaken. The laws themselves feel like boundaries meant to contain chaos, not to protect life, but to prevent the cosmos from unraveling. Life, in contrast, grows upward like a fragile stalk of grass pushing through a fracture in stone. The stone was never designed for it. It simply didn't close the gap fast enough. You're listening to Whispers of the Universe. If you're gentle enough to leave a small sign of your presence, perhaps a like or a subscription, you help this quiet place remain alive a little longer. The idea that the cosmos fits us is deeply misleading. Everything we know suggests the opposite. Gravity, for instance, is absurdly weak, 10 to the power of negative 39 times weaker than the electromagnetic force. A force of that weakness makes forming stable, long-lived stars almost impossible. Too strong, and the universe collapses before structure forms. Too weak, and stars cannot ignite. It's a razor-thin path, and we somehow walk it. The mass difference between protons and neutrons, just 0.1%, dictates whether atoms can exist at all. A slightly different value, and hydrogen would decay or fail to bind, and the chemistry of life would never take shape. Even the strong nuclear force is tuned with eerie precision. Shift it a fraction of a percent, and carbon cannot form in stars. Shift it another fraction, and oxygen disappears. The foundations of every organism collapse instantly. These numbers appear gentle at first glance, but they are not friendly. They sit at the edge of annihilation, poised in a way that feels less like hospitality and more like a knife balanced upright on a stone, steady only because nothing has disturbed it yet. If the universe were evaluated as a habitat, it would fail every metric except one. It occasionally allows life, and even then, only barely. The cosmos is more void than matter, more collapse than construction, more entropy than order. Life is the exception, written in faint ink. The clearer it becomes that what we call fine-tuning is not tuning for life at all. It is tuning for the stability of physical laws, and life simply occupies one of the rare islands those laws accidentally permit. Cosmic background radiation still carries the afterglow of the Big Bang. A temperature of 2.725 K, cold enough to kill any living system in seconds. Across almost all of space, you would freeze, suffocate, and disintegrate simultaneously. Not because the universe is cruel, but because it is not built with the mechanisms that life requires. Allow yourself to imagine the Milky Way from the outside, a glowing swirl of stars, beautiful but inhospitable. Only a tiny fraction of its regions fall within stable temperature ranges. Only a subset of those have metal-rich stars. Only a few of those stars have planets in habitable zones, and even fewer worlds remain calm long enough to sustain biology. This is not abundance. This is survival by coincidence. Across the cosmic web, There are trillions of galaxies, each one a storm of violent collisions, collapsing gas clouds, explosive births of stars, and radioactive debris that could erase an entire biosphere in minutes. Between galaxies, there is nothing, just dark energy stretching space-time thinner each day. To say the universe is not for us is almost an understatement. The more accurate statement is, we are intruders, occupying a temporary pocket where the rules have not yet tightened. Entropy, the universe's one-way drift toward disorder, always wins. Complexity is fragile. Atoms themselves are slowly moving toward a final, inevitable stillness. The cosmic expansion accelerates, pulling distant galaxies beyond visibility, stripping even light of its ability to connect distant regions. Everything tends toward disassembly. Life tends toward structure. The universe tends toward undoing structure. They move in opposite directions. So when we consider how lucky the universe seems, how finely tuned, we must ask, tuned for what? For stability of equations, perhaps. For the balance between expansion and collapse. For predictable behavior of particles, but not for warmth, and not for comfort, and not for anything resembling a welcoming home for biological beings. We stand in a brief alignment, a narrow window where the universe is cool enough for chemistry, but still energetic enough to allow stars to shine. A window that closes eventually. Stars will dim, matter will decay, temperature will approach absolute zero. In the far future, even the memory of life may fade into the uniform dark. We live not in a universe crafted for our existence, but in a universe that simply hasn't erased us yet. And that realization leads us quietly toward a heavier question, one that sits at the edge of logic and fear. If the laws of physics do not favor life, why do they align just enough for it to emerge anyway? Is life the unintended byproduct of a system indifferent to its survival? Or does the narrowness of possibility reveal something deeper about how reality selects its own outcomes? The thought lingers, soft but pressing, as if the universe is whispering through its equations, telling us that our existence is not part of its design, but a side effect, a flicker, a brief warmth inside a machine built for cold. And that whisper becomes the bridge to the next question, one that shapes the entire journey ahead. If the universe is not designed for life, then what, exactly, is it designed for? The answer waits in the quiet dark of what comes next. The question that lingered at the end of the last thought, the question of what the universe is actually shaped for, does not loosen its grip as we go deeper. Instead, it pulls tighter, revealing something quietly unsettling. The laws of nature behave as if they were never meant to accommodate life in the first place. Not because they oppose it, but because they do not recognize it. They draw the outlines of reality with a precision that leaves almost no room for the fragile complexity we call living. They sculpt a cosmos where the natural state of matter is isolation, simplicity, and decay. A place where stability is rare, and where the slightest deviation from a narrow set of conditions pushes everything back toward disorder. It begins with entropy, the universal drift toward increasing randomness. Entropy does not work against life out of intention. It simply follows its own gradient, a pressure from deep time that always nudges matter toward simplicity. Every system that builds order must pay a cost. Every breath, every chemical reaction, every spark of metabolism is purchased by feeding energy into the tide. Life is, by nature, a brief resistance to that tide. But that resistance is permitted only where other rules align, rules that are not themselves aligned with life. The strength of gravity, the charge of the electron, the binding energy of the strong nuclear force. Each one sits within a razor-thin interval where stars can form without collapsing, where atoms can bond without falling apart, where chemistry can climb out of the dark long enough to build cells, tissues, consciousness, move any parameter by a fraction, and the corridor of possibility closes. Not gradually, completely. The universe functions like a labyrinth in which most paths end abruptly. We happen to drift into one of the few corridors that continues for a short distance, letting matter organize itself into something capable of observing the labyrinth at all. But step outside that corridor, and the walls turn solid. Across the cosmos, There are vast expanses where the basic behavior of matter undermines every attempt at complexity. In some regions, gravity dominates so strongly that gas clouds collapse too quickly for planets to form. In others, radiation is intense enough to shatter molecular bonds the moment they assemble. Elsewhere, the cosmic environment is so sparse that atoms rarely collide at all. Chemistry cannot occur because matter is simply too thin to meet itself. These dead regions are not rare pockets, they are the majority. Life survives only in the slim minority, where forces balance in a way that is neither too violent nor too inert. Imagine looking at a galaxy from above. Its luminous spiral arms seem calm, almost peaceful. But zoom closer, and the calm dissolves. Supernova shockwaves ripple through the arms, sterilizing everything in their path. Magnetic storms erupt on the surfaces of stars, sending lethal flares across entire systems. Planetary orbits drift slowly, subtly, under gravitational nudges from passing bodies. Asteroids simmer in the dark, waiting for unpredictable collisions that can erase billions of years in a day. Stability, for life, is not given. It is borrowed temporarily from a universe that does not care whether the loan is ever repaid. Even our own solar system is a narrow slice carved from instability. Jupiter's gravity shields us from some objects while redirecting others toward us. The moon stabilizes Earth's tilt enough to prevent chaotic climate swings. Our sun burns steadily only because it is the right mass to fuse hydrogen calmly rather than erupt violently. Remove any one of these supports, and Earth becomes uninhabitable. This delicate interplay suggests something important. Life depends on structures that the universe forms reluctantly. Structures that emerge not because the laws encourage them, but because the laws do not prevent them in absolutely every case. Cosmologists sometimes describe the universe as permissive, but that word is misleading. The universe is permissive only in the way a crack in stone is permissive, providing just enough space for a thin blade of grass to rise. The stone was never designed for it. The crack was never intended, and the grass survives only until the next shift seals the gap. There is a deeper layer to this imbalance, found in the very constants that shape atomic behavior. The mass ratio between protons and neutrons, the strength of the electromagnetic interaction, the curvature of space itself, each one sits at a value that allows complexity to develop, yet pushes continually against it. Take the strong nuclear force. If it were slightly weaker, nuclei would fail to bind. The universe would contain only hydrogen too simple for life. If it were slightly stronger, fusion inside stars would proceed too rapidly, burning them out long before planets could form. In both cases, the cosmos becomes a theater without actors, or consider dark energy, the mysterious pressure accelerating the universe's expansion. If its value were higher, galaxies would never condense. Matter would disperse into eternal loneliness before structures could form. If it were lower, the universe would collapse back into itself long before biochemistry could ignite. These values are not balanced for life. They are balanced for consistency. Life simply fits inside the margin, and that margin is thin enough that even small fluctuations can erase it. Physicists have long suspected that vacuum energy, the baseline level of the universe's fields, might not be perfectly uniform. If this energy shifts in certain regions, even by tiny fractions, particle interactions would change. Atoms might form differently, or not at all. Chemistry would either behave unpredictably or cease entirely, leaving matter in a state that appears familiar from afar but collapses upon inspection. These theoretical zones occupy an uneasy place in cosmology. We cannot see them directly, but mathematics allows them, and the laws do not forbid them. If they exist, they are places where the universe quietly redraws its own blueprint, not violently, like a supernova, but silently, by altering the rules under which existence holds together. In those places, life is not killed. It is unmade, no explosion, no radiation, just a shift so deep that the conditions for alive no longer have meaning. This possibility underlines a truth more sobering than any cosmic disaster. The universe is not hostile to life in the way predators are hostile to prey. It is hostile in the way oceans are hostile to flames. The ocean does not hunt the flame, it simply does not allow it. And life, ultimately, is a flame. A controlled burn of energy against the chill of the void. But even flames flicker only where oxygen gathers. Move slightly away from the narrow zone where fuel, heat, and air converge. And the flame vanishes not because something extinguished it, but because the environment did not sustain it. The cosmos is almost entirely an environment where the flame cannot take hold. Seen from this angle, the emergence of life is not evidence of cosmic generosity. It is evidence of how rarely the ruling conditions slip. That rarity explains why biology appears so late in cosmic history, after stars enriched space with heavy elements, after planetary disks cooled, after the first violent ages passed. Only when the universe relaxed its earliest pressures did complexity have a chance to try. And even now, that chance is temporary. Entropy continues its long ascent. Stars drift and dim. Galaxies move apart. Temperature gradients flatten. Chemical potential fades. The universe will not collapse life. It will simply wait for the processes that sustain it to diminish. Yet inside this immense indifference, life persists for now, where the pressures line up just gently enough for it to grow. In these rare places, chemistry becomes memory. Memory becomes intention. And intention becomes the quiet awareness that senses the cold shape of existence. There is something haunting in that awareness. We understand now that life is not the default, but the interruption. Not the natural state, but the fleeting exception. And within that exception, a strange clarity emerges, subtle, almost imperceptible. The sense that what survives does so, not because the universe allows it freely, but because the narrow corridor through which it moves has not yet closed. A corridor that continues forward, dimly lit, its end unseen, its shape defined not by invitation, but by the fragile alignment of forces that hold for one more moment, and one more after that. As long as the balance remains intact, there is a quiet strangeness that appears once you look long enough at the structure of the cosmos. The laws of nature, so rigid and universal in principle, do not operate with the same softness everywhere. In most places, they behave predictably, almost mechanically, but there are regions where something shifts subtly, silently, and the ordinary behaviors of matter begin to wander from the patterns we know. These places do not announce themselves. They do not glow or ripple or distort the fabric of space in dramatic ways. They simply exist as territories where the familiar scaffolding of physics becomes less stable, and the delicate alignments required for complexity slip out of tune. Life never begins there. It cannot. And not because these regions are violent or chaotic. Some are remarkably calm. So calm, in fact, that nothing holds together. The idea that the universe behaves identically everywhere is comforting. It suggests that what we learn in one corner applies to all corners. But reality is quieter and stranger. The laws are universal. Yet the conditions that give them shape vary enough that the same rules can produce very different worlds. Some fertile, some barren, some fundamentally incompatible with complexity. To understand these dead regions, imagine first a place where nothing actively destroys life. There is no radiation, no collapsing star, no catastrophic impact, just an emptiness so perfect, so absolute, that atoms almost never meet. In such a place, chemistry has no beginning. Bonds never form, molecules never gather. Temperature hovers at the edge of meaning. Matter drifts endlessly, without touching enough of itself to change. This emptiness makes up most of the universe. But there are deeper forms of deadness regions, where the uniformity of space hides delicate imbalances. Zones where slight variations in density, background fields, or vacuum energy tilt the probabilities just far enough that matter behaves differently from what biology requires. Picture a region where electrons adhere a little too loosely to their nuclei. Atoms there would still exist, but their bonds would fail unpredictably. Complex molecules would tear themselves apart faster than they could form. A single base pair of DNA, if it ever assembled, would not survive long enough to be recognized as structure, Or imagine a region where the opposite happens, where electrons cling a little too tightly, locking chemistry into rigid, lifeless patterns. The atoms feel familiar, yet refuse to cooperate in the dance that biology depends on. These places are not theoretical curiosities. They arise naturally from the interplay of quantum fields, cosmic expansion, and the turbulent history of matter formation. As the early universe cooled, phase transitions rippled outward shifts in the structure of spacetime itself. These transitions did not complete perfectly everywhere. Cosmic inflation stretched tiny irregularities into vast territories that now drift silently across the cosmic web. We cannot see these regions directly. Their differences do not shine, but we can infer them from the mathematics of the vacuum, from the sensitivity of particle interactions, from the possibility that the universe contains domains with slightly altered values of the same underlying fields. Physicists call them metastable regions, places where space is perched on the edge of a different state, waiting, however, patiently for a fluctuation large enough to tip it into a new configuration. If such a transition ever occurs, it would propagate outward at nearly the speed of light, rewriting the rules of physics as it expands. Within that wavefront, atoms would rearrange or dissolve, stars would falter. Everything built under the old rules would become incompatible with the new. No living thing could survive such a shift, not because the transition is violent, but because it is absolute. Yet even without such dramatic events, the existence of metastable zones is enough to create territories where life cannot appear, not due to destruction, but due to non-compatibility. Life requires precision, and precision requires a foundation that holds steady. Where the foundation wavers, even slightly, the door closes. These are the deeper dead regions, not voids, not hazards, but misaligned pockets of reality. But the universe contains another category of deadness more familiar, but just as unforgiving. In dense clusters of matter, gravity becomes overwhelming. Gas clouds collapse too quickly. Stars accelerate from formation to detonation within million-year intervals far shorter than the time required for planets, weather, oceans, and the long chemical patience that evolution demands. Everything is compressed, heated, pushed past the threshold where complexity can take root, move closer to massive stars, and light becomes a weapon. Ultraviolet radiation strips electrons from atoms. X-rays slice through molecular bonds. Gamma rays rearrange nuclei. Even if a world had oceans, continents, and atmosphere, its surface would be continuously sterilized. Life is not merely discouraged there, it is fundamentally incompatible. And deeper still are the gravitational abysses, territories near neutron stars and black holes, where matter is stretched and broken by tidal forces so extreme that even atoms cannot remain intact. In these places, the fabric of spacetime curves so sharply that time itself slows, pressure rises until matter collapses inward, and the rules of quantum mechanics and gravity collide in unresolved tension. Life requires stability. These regions provide only extremes. The most unnerving dead regions, however, are not the brightest, hottest, coldest, or emptiest. They are the ones that appear deceptively ordinary worlds, circling quiet stars, atmospheres thick enough to soften radiation, surfaces stable enough to hold oceans, and yet, for reasons hidden in their deeper physics, they do not support the chemical self-assembly that gives rise to life. Sometimes the temperature is right, the pressure is right, the orbit is stable, the composition is promising, and still nothing emerges. Billions of years pass in silence. It is tempting to imagine that life is simply rare, slow to arise, easily extinguished. But the patterns suggest something more structural. In many places, the basic building blocks do not interact in the right sequence. Catalysts never form. Organic compounds degrade too quickly. The symmetry of water molecules might be off by a fraction. The UV window needed for early chemistry may not open at the right intensities. Life depends on a delicate choreography. Where the timing falters, the dance never begins. Some researchers speculate that subtle variations in local physics, minute shifts in constants or field strengths, may influence these failures. If so, Then these seemingly Earth-like worlds are part of the same family of dead regions, places where the rules shift just enough to close the narrow window through which life must climb. The silence of these worlds deepens the sense that existence unfolds inside a universe that never meant to cultivate life broadly. It formed a structure that is mathematically stable, thermodynamically consistent, and physically coherent, but not biologically abundant. The cosmos provides no guarantee that life should be common. It only guarantees that the laws remain intact. Everything else is incidental. And when you step back far enough, a pattern becomes clear. The universe creates complexity only in rare, precarious pockets, and everywhere else, it favors either isolation or collapse. Matter drifts into arrangements that are either too simple to host life or too extreme to maintain it. The corridor that allows biology is a thin contour on a landscape shaped by forces that do not consider it. This understanding shifts something inside the mind. The assurance that life might exist everywhere dissolves. What replaces it is quieter, heavier. The sense that living worlds are not sprinkled generously across space, but concealed, hidden, fragile, in a universe that expresses itself most naturally through emptiness and flame. And yet, paradoxically, in recognizing the breadth of these inhospitable zones, one also becomes aware of how extraordinary the rare places are where matter holds steady, where energy flows gently, where chemistry remains just restless enough to experiment with form. Those pockets of balance do not erase the vastness of dead regions, but they trace a faint, continuous line through the dark, a line along which complexity survives long enough to become aware of its own improbability. And in that faint line, that narrow thread of possibility stretched across a mostly indifferent cosmos, one begins to sense how unlikely it is for anything living to ever open its eyes at all, and how delicate the conditions must remain for those eyes to stay open a moment longer. There is a quiet irony that emerges once you understand how many regions of the universe are unsuitable for life. Even in the rare places where gravity balances gently, where chemistry can persist, and where the laws hold steady. The very thing that reveals the cosmos to us, the thing that carries information, warmth, and time, is also one of the most efficient forces of destruction. Light, in all its radiance, behaves like a double-edged instrument. It illuminates, but it cuts. It carries messages across billions of years, but the closer you stand to its source, the more effectively it erases what tries to grow. It is through light that we know the universe exists at all. It is through light that we measure distance, decode structure, reconstruct history. Every star is both a beacon and a warning, because embedded within the softness of starlight is a spectrum that includes forms invisible to our eyes, but devastating to the fragile scaffolding of life. Ultraviolet rays fracture the delicate architecture of DNA. X-rays penetrate deep into molecular chains, severing bonds that cells rely on. Gamma rays, a rare but ancient presence, possess enough energy to disrupt the very nuclei that anchor atoms. The night sky appears calm only because our eyes filter out the violence. Imagine for a moment that you could see every wavelength at once. The darkness above would ignite into storms of radiation. Filaments would pulse with energetic currents. Invisible tides would sweep across space like weather, carrying enough power to sterilize entire continents if they struck a living world without protection. Life emerges only where the destructive parts of this spectrum are filtered, softened, or blocked. Earth manages this through an improbable combination of factors. A magnetic field born from a molten core, an atmosphere thick enough to scatter high-energy photons, and a star that emits most of its light in a narrow, bio-friendly band. Alter any one of these, and the surface becomes lethal. We often imagine sunlight as a nurturing presence, warmth, growth, comfort, but at the level of physics, sunlight is a stream of charged particles and photons, energetic enough to tear apart the very molecules that make us feel alive. Plants and animals exist because Earth has constructed a shield out of magnetism and chemistry, a soft envelope around a violent source. This shielding is not common. It is rare. It is an exception. Out in the broader universe, light is not gentle. It is a form of pressure, a current of pure energy that flows without hesitation, without regard for what stands in its way. The most dramatic examples are gamma-ray bursts, brief, intense flashes that erupt when massive stars collapse or collide. In a fraction of a second, they unleash more energy than entire galaxies produce over long spans of time. If one were to happen within a few thousand light-years of Earth, it could strip away the atmosphere, leaving the ground exposed to cosmic radiation. Life would not fade, it would vanish. Even ordinary starlight can be lethal if a planet orbits too closely. A slight migration inward, and oceans evaporate. A slight drift outward, and water freezes solid. Life exists within a razor-thin zone, the habitable region, not because stars are mild, but because Earth occupies the precise distance where light warms without burning. Outside that zone, light becomes indifferent again. In dense star clusters, the intensity of radiation is so high that any attempt at biology is extinguished before it begins. In young systems, ultraviolet flares erupt wildly, sterilizing the surfaces of newborn planets. Around red dwarfs, the most common stars in the universe, magnetic storms blast their worlds with bursts of radiation that make long-term stability impossible. The universe's most abundant stars, therefore, are also some of the least welcoming. Even in the vacuum between worlds, photons travel freely, carrying the memory of violent events, supernova remnants, shockwaves, ionized gas trails. Cosmic rays charged, high-energy particles launched from ancient catastrophes pierce through matter like invisible needles. These particles, traveling near the speed of light, can disrupt DNA with a single impact. They drift everywhere. They pass through planets, through oceans, through bodies, even through us. Life on Earth survives them only because of the layers of shielding provided by the planet's magnetic field and atmosphere. Without this dual protection, the surface would be constantly bombarded. The faint warmth of starlight that reaches our eyes is only the quietest fraction of the radiation being released. This duality, the beauty of light and its lethality, reveals something deeper about the universe. Information and destruction are woven from the same fabric. The photons that let us see a distant galaxy are cousins of the photons that tear molecules apart. The same electromagnetic force that binds atoms together also fuels the radiation that destabilizes them. The very mechanism that makes stars shine is the mechanism that causes them to burn, flare, and eventually explode. Nothing in the universe is purely gentle. Everything carries sharpness within it. Light is the clearest example because it exposes not only the cosmic landscape, but also its dangers. When it travels across space, it encounters no resistance. When it strikes matter, it rearranges electrons. When it interacts with chemistry, it writes or erases structure with equal ease. If conditions are favorable, light becomes a catalyst for life. If conditions shift slightly, light becomes the reason life cannot form. This sensitivity underscores the precariousness of existence. Life depends on a universe that provides energy, but not too much. Complexity depends on environments that allow photons to move freely, but not violently. And planets depend on stars that shine steadily, but not aggressively. Most stars do not meet these criteria. They flare, pulse, dim, rotate irregularly, switch magnetic cycles, and erupt with little warning. Even our Sun, often portrayed as stable, launches billion-ton clouds of charged particles that could strip an atmosphere bare if they struck a world without protection. We exist because Earth carries a shield. And that shield exists only because a series of geological and magnetic coincidences happened in the right sequence. But stepping back, one sees a broader pattern. The universe is not primarily a place of warmth. It is a place of illumination, and illumination is indifferent. The glow of stars is a side effect of fusion, a process that destroys matter at unimaginable rates. A star shines by breaking itself apart, and the light we see is the signal of that disassembly. Life uses that signal carefully, taking just enough energy to sustain itself, while hiding behind barriers strong enough to deflect the rest. The thin balance between nourishment and annihilation shapes every biological system. Plants stretch toward light, but only through pigments that filter its most dangerous wavelengths. Animals see within a small, safe window. Cells repair themselves continuously because photons always leave scars. Life survives not because light is kind, but because life adapts to its harshness. And yet, even adaptation has limits. There are thresholds of radiation, intensity, frequency, and duration beyond which no biological structure can persist. These thresholds define the outer boundaries of habitable zones, not merely in space, but in time. Stars evolve, their brightness changes, their spectra shift. What is gentle today may be lethal tomorrow. In the long arc of stellar lifetimes, every star eventually grows too bright or too unstable for life to continue. The soft equilibrium that planets rely on is temporary. The universe does not stop shining, but it does stop nurturing. This realization reshapes the way light is understood. It is not the universe's generosity. It is its language, a language spoken in photons that carry both creation and erasure. To become aware of this language is to feel the strange tension at the heart of existence. We see because stars burn, we live because Earth filters, and we survive only because the destructive part of the spectrum is kept at bay for a fleeting moment. When the filtering ends, the meaning of light changes again. And in the stillness that follows that thought, one begins to sense how narrow the space truly is, where illumination can warm without cutting, where chemistry can rise without collapsing, and where living things can look toward the sky without fear of being undone by the very glow that reveals it. In that fragile space, the universe feels momentarily softer, not because it intends softness, but because its sharpness has, for a brief interval, diminished enough to let something grow. It becomes clearer, after spending time with the cruel brilliance of light, that the universe does not only challenge life through radiation. Light is only one of the many agents through which the cosmos reminds us that living things endure here only by exception. When you zoom out far past the level of photons, past the flicker of starlight, past even the cosmic voids, you begin to see a deeper truth. Nearly every square inch of the universe is unfit for life, not merely inconvenient, not merely difficult, but fundamentally incompatible. There is no natural refuge out there, no inherent sanctuary. The universe does not offer safe spaces by design. It offers them through accident. Life on Earth thrives behind layers of protection, hidden from the full violence of space. But strip those protections away, and the environment reveals its original character, a character defined not by hostility, but by pure indifference, an indifference so complete that survival becomes impossible without shelter. To understand this indifference, you must first imagine what space actually is. Not the poetic darkness above our atmosphere, but the vast physical environment that occupies almost all of reality. Space is not empty in the ordinary sense. It is empty in a way that annihilates biological forms. It contains no air, no warmth, no pressure. In vacuum, water does not evaporate. It boils instantly. Without pressure, gas exchange stops. Membranes rupture. Blood turns to vapor. The human body does not explode, but it cannot remain alive for more than seconds. This is the baseline condition of the cosmos. A temperature near absolute zero, radiation drifting without obstruction, extreme emptiness, dissolving the foundations of biology. Earth is not representative of the universe. It is an exception, a rarity, a carved-out pocket. Most planets, even when rocky and Earth-sized, stand far outside the safety of habitability. Some orbit too close to their stars, their surfaces locked in molten seas. Some orbit too far, their oceans frozen in darkness. Many possess atmospheres too thick or too thin, or none at all. Some worlds rotate so slowly that days last months, baking one side while the other freezes. Others tilt too violently, dragging their climates into extremes that no chemistry can adapt to. Even the notion of a habitable zone is misleading. It assumes that distance from a star is the primary determinant of comfort, But the truth is harsher. Temperature alone cannot create safety. A world may sit at the perfect distance and still be uninhabitable because its magnetic field is absent, because its geology fails to recycle carbon, because its star sends unpredictable flares, or because its early history sterilized the surface before life had a chance to gain complexity. Safety is not a region. It is a rare alignment of geological, atmospheric, chemical, and stellar conditions, all converging for a brief period. Step outside that alignment, and safety dissolves. The more you examine the solar system, the clearer the pattern becomes. Venus has the right size, the right amount of material, and the right position relative to the Sun for life to be possible. Yet its atmosphere transformed into a dense shroud of carbon dioxide, trapping heat until the surface reached temperatures capable of melting lead. Mars, once warm enough for rivers to flow, lost its magnetic field, letting the Sun strip away its atmosphere molecule by molecule. What remains is a world too cold, too dry, too barren. These are not mistakes. They are the natural outcomes of the laws that govern planetary evolution. Earth avoided both fates by an improbable combination of factors: an internal dynamo that generates a magnetic field, a plate tectonic engine that regulates atmospheric gases, a moon that stabilizes its rotation, oceans deep enough to distribute heat, but not so deep as to suppress land formation. These features are not typical. They are extraordinary. Move beyond the solar system, and even this delicate balance becomes rarer still. Most planets orbit red dwarf stars far dimmer than the Sun, yet far more violent in their eruptions. Their habitable zones are so close that planets become tidally locked, with one hemisphere scorched under constant daylight and the other buried in perpetual night. For life to emerge there, it must endure stellar flares that can sterilize entire surfaces in minutes. Again, this is not hostility. It is the natural shape of stellar physics. The cosmos operates on scales, and with energies that dwarf biology's tolerance. The environments that remain calm enough for life are fleeting, narrow, tucked into the edges of stability. Even on worlds that might support life, the timeline of safety is short. Stars evolve, planetary interiors cool, magnetic fields weaken, chemical cycles stall, atmospheres erode. Safety has an expiration date. Earth itself is temporary. The Sun will grow brighter over the next billion years, and the planet's oceans will evaporate. Long before the Sun becomes a red giant, Earth will pass through stages that eliminate its habitability. The atmosphere will thin, the surface will heat, and the delicate equilibrium that life depends on will collapse. Life here persists not because the universe favors it, but because conditions have not yet drifted too far from balance. This transience extends beyond stars and planets. Even the galaxies themselves change. Over time, galaxies collide, reshaping their internal structures. Star formation ceases. Gas supplies diminish. Radiation becomes unevenly distributed. Regions that once supported the quiet stability needed for life may shift into forms that no longer permit it. The farther you look, the more the universe seems to be built around processes that destabilize rather than sustain. Gravity condenses matter until it collapses. Radiation strips away the fragile. Thermal gradients widen and narrow unpredictably. Magnetic fields bend and fracture. Stellar winds tear across space. To search for safety in such a universe is to search for calm weather in a storm whose winds span billions of miles. Even the interstellar medium, the space between stars, is not gentle. Ionized hydrogen drifts through it. Cosmic rays streak across it. Temperature differences carve invisible boundaries. Should a planet drift beyond the protective bubble of a star's influence, it becomes exposed to unfiltered radiation that would sterilize any surface life instantly. Safety exists only behind shields, within atmospheres, around stable stars, and under circumstances that persist only briefly. To understand how narrow this path is, consider that life requires liquid water for long periods, a stable range of temperatures, shielding from radiation, a consistent source of energy, chemical gradients, atmospheric pressure, a geologically active interior, and relative calm in the surrounding environment. Each factor depends on dozens of underlying conditions. Each condition depends on physical parameters set in the earliest moments of the universe. Each parameter exists on a knife edge of possibility. If any step fails, the entire chain collapses. The more deeply you analyze this chain, the more astonishing it becomes that any world remains safe long enough for life to emerge, let alone persist long enough to evolve intelligence. Safety is not a natural state, it is a negotiated one. Earth negotiates it continuously. Volcanic outgassing replenishes the atmosphere. Plate tectonics recycles carbon. The magnetic field redirects solar wind. The oceans buffer climate swings. The atmosphere blocks ultraviolet radiation. Remove one component, and the world becomes unrecognizable. If safety must be engineered by nature so carefully, it becomes clear why the universe provides so few havens. Life exists only where shielding, stability, and timing align for a moment, and these alignments are fragile. Space does not want life any more than it wants storms or silence. It simply does not adjust itself for the things that arise within it. The laws remain unchanged. The conditions drift. Safety flickers in and out like a candle caught in the currents of a vast, cold room. And in recognizing this, something shifts internally. The feeling of belonging in the universe softens. You begin to see that what we call home is a temporary shelter built inside a cosmos that offers no guarantees. Yet there is also a quiet wonder in this fragility, a sense that life, in carving out safety where none exists, reveals something remarkable about itself. It adapts, it endures, it assembles pockets of warmth inside an ocean of cold. It rises, again and again, even in the brief intervals where the universe stabilizes long enough to allow it. Perhaps safety is not a place. Perhaps it is a moment held gently between forces that neither intend to protect nor intend to destroy, forces that simply operate, and in their operation create the narrow conditions under which something living can appear, breathe, change, and imagine. And within that moment, even if fleeting, life finds a way to recognize the vastness around it without dissolving beneath its weight. It senses how small the sanctuary truly is, yet remains here, suspended in the delicate calm between extremes, aware of how rare it is to inhabit a world that feels, even briefly, like a place that shelters more than it erases. Once you understand how little space the universe offers to life, another realization begins to surface, quieter but heavier, as if emerging from beneath the flow of everything that has ever lived. Even if a world finds a safe place in the cosmic expanse, even if light softens enough, even if chemistry aligns perfectly, there is still a deeper constraint woven into the structure of reality. Time, not the poetic sort, not the human sense of days slipping between fingers, but the cosmic version measured in epochs, in the slow breathing of stars, in cycles so long that life occupies only a thin, flickering moment within them. The universe gives safety rarely, but more importantly, it gives it briefly. Every star, every planet, every stable environment has an expiration date written into its physics. The cosmos is made of processes that move at scales far larger than biology can tolerate. And when you compare the timelines, a troubling mismatch appears. One that makes life feel not just improbable, but rushed. Consider a star. To us, it seems eternal, a steady presence across generations. But a star is simply a machine running through its fuel, balancing gravity against nuclear pressure. Its lifespan depends entirely on its mass. Massive stars burn too quickly, millions of years, not enough time for complex biology to assemble. Small stars burn too erratically, flare after flare, sterilizing their worlds before life can recover. Only stars like the sun strike a fragile middle ground. Not too bright, not too erratic, not too short-lived. And even then, their stability is temporary. A star brightens with age. Its luminosity drifts upward. Its temperature shifts. Its spectrum changes. Life must arise, diversify, and flourish within a narrow slice of that timeline. A slice so thin it could be missed entirely. if chemical evolution proceeds too slowly or environmental stability falters for even a moment. For Earth, that window spans a few billion years. For the universe, it is a blink. But the mismatch deepens when you look at planets. Planets cool faster than stars evolve. Their magnetic fields can weaken long before their suns become unstable. Their atmospheres can be stripped away in a geological instant. Their surfaces can become either frozen or overheated within time spans far shorter than the development of complex life. Even the presence of liquid water, a requirement for biology, is not stable across cosmic time. Water relies on atmospheric cycles. Cycles rely on temperature gradients. Gradients rely on internal heat and stellar output. Shift one variable, and oceans either evaporate or solidify. Time, for worlds, is a narrowing corridor. It opens. It remains calm for a while. Then it contracts until life cannot follow. Biology moves slower than planets change. For life to evolve intelligence, it needs hundreds of millions of years of climatic stability. It needs continents that do not rearrange too violently. It needs seas that do not boil or freeze beyond recovery. It needs atmospheric chemistry that remains within a narrow band while metabolism becomes more intricate, generation by generation. But geological time is restless. Climate cycles swing. Axial tilt shifts. Orbital eccentricity oscillates. Impact events interrupt evolution. Volcanoes can choke skies for centuries. Ice ages sweep across continents. Life is forced to adapt faster than the planet destabilizes. Sometimes it succeeds. Often it does not. Most species vanish before their world becomes unsafe. Their disappearances leave no trace across cosmic time. Even on Earth, where conditions have been unusually stable, extinction is the natural rule, not the exception. 99% of all species that have ever lived no longer exist. This fact reveals something profound about time, as the universe experiences it. Stability long enough for intelligence is astonishingly rare. It requires a planet that remains habitable longer than average, orbiting a star that evolves more slowly than average, under geological conditions calmer than average, with a biosphere resilient enough to survive swings sharper than average. Every part of that chain contains a timer, and the timers do not match. Even if a world achieves balance for a while, a few million years of relative calm life often needs more. Simple organisms arise quickly, but complexity drags forward slowly, requiring patience from a universe that does not typically pause. Multicellular life on Earth took billions of years to appear. Intelligence took even longer. Civilization, as we know it, occupies less than a breath of cosmic history, barely a few thousand years inside a universe that has existed for almost 14 billion. It is not only that time is short, it is that biology requires long spans of calm that the universe almost never supplies. There is another layer, the future. Stars will not remain stable forever. Planets will not keep their atmospheres forever. Magnetic fields will not last forever. Even the molecules inside living cells are susceptible to subtle shifts in cosmic conditions that accumulate slowly but unavoidably. Eventually, every safe zone closes. Look at Earth's timeline more closely. The sun brightens by roughly 10% every billion years. That rise is enough to push Earth's climate into a runaway greenhouse state. Oceans will begin to evaporate. Carbon cycles will break down. Atmospheric composition will drift too far for life to regulate. Plants will die. Animals will follow. The biosphere will collapse. All while the sun is still considered stable. Even before the sun reaches this phase, fluctuations in solar output may destabilize climate more sharply than biology can adapt to. Earth has endured ice ages, global volcanism, asteroid impacts, magnetic reversals, each one a reminder of how thin the margin is for life to keep its foothold. Time does not need to be violent to eliminate life. It simply needs to continue. The acceleration of the universe's expansion adds another constraint. As galaxies drift apart, interstellar gas thins, star formation slows. The cosmic inventory of energy available to future life shrinks. There will come a time when stars become rare, then faint, then cold. A time when planets freeze permanently. A time when black holes dominate, not starlight. A time when the universe is too thin, too dark, and too quiet to support complexity. Life arises only within the first few percent of cosmic time. After that, the universe becomes inhospitable, not by violence, but by exhaustion. The era in which life can exist is not only narrow, it is temporary. This impermanence, written into the equations of matter and energy, reveals something humbling. The universe did not set aside eternity for life. It allowed a moment, one moment, a brief interval where stars shine steadily enough, where matter remains complex enough, where chemistry stays restless enough to produce beings capable of noticing the passage of time at all. Even intelligence is caught within a shrinking window. The technologies that civilizations might use to extend their survival require energy sources that the universe will eventually deny. Black holes evaporate, stars fade, particles decay, temperature sinks toward equilibrium so absolute that nothing can resist it. Time erases everything, not out of malice, but out of thermodynamic certainty. And yet, despite this certainty, life persists during its moment. It builds languages, memories, structures, and meaning inside the narrow corridor where time, for a fleeting stretch, holds still just long enough for thought to form. There is a strange beauty in this. The idea that life is not meant to fill the universe, only to pass through one of its rare, calm intervals. That consciousness is not a destination of cosmic evolution, but a visitor arriving briefly between the violent birth and the quiet death of stars. Life's timeline is not the universe's timeline. It is a moment carved inside it. And when you feel that moment, not as a metaphor, but as a physical truth, it changes the sense of what it means to exist. You begin to understand that living things are synchronized with an interval that the universe barely notices, that the span in which eyes can open, minds can evolve, and civilizations can wonder is astonishingly short compared to the story unfolding on scales too vast for biology to witness. Yet inside that shortness, life finds room enough. Room to expand, to think, to adapt, to reflect, room to construct meaning where the universe provides none. Room to leave patterns in the dark, even if those patterns are temporary. The window may be brief, but within it, something remarkable unfolds. A delicate architecture of memory and intention suspended inside a universe that flows indifferently past it, unaware that, for a moment, in one small place, time held itself steady long enough for something living to arise and notice. As the thought settles that life occupies only a short permission of time, another question begins to rise gently at the edge of the mind. A question about what holds the universe together during that fragile interval. Because time is not the only force that narrows the corridor for life. Something deeper, quieter, and far more enigmatic guides the structure of everything we see. Gravity is its language, but gravity is not its source. The architecture of the cosmos, galaxies, clusters, filaments, does not arise from the matter we touch or understand. The ordinary atoms that form stars, planets, oceans, and cells account for almost nothing of the universe's mass. They are the surface of a structure whose foundation is invisible. There is something else out there, something massive, something silent. Its presence outweighs everything familiar by a factor of 5. Without it, galaxies would not hold together, stars would drift apart, planetary systems would never have formed. The universe would be a loose, dispersing cloud, too unstable for complexity to arise. This unseen substance, dark matter, acts as the scaffolding of the cosmos. It creates gravitational wells into which normal matter falls, cooling and condensing, forming the structures we know. Yet, for all its importance, dark matter interacts with life, not through chemistry or light or any of the mechanisms biology depends on, but solely through gravity. It does not collide with atoms. It does not bind or break molecules. It does not participate in the delicate laws that make life possible. Dark matter simply passes through everything, unnoticed, unaltered. Hundreds of billions of particles may cross your body each second. They leave no trace. They do not disturb a single cell. They drift, ghost-like, through matter, as if it were not there. But their collective presence shapes the universe in ways more fundamental than anything ordinary matter can accomplish. The spiraling arms of galaxies trace the gravitational imprint of dark matter halos, vast spherical structures surrounding every star system. These halos extend far beyond the visible edges of galaxies, silent, enormous, ancient. Life emerges only inside the spaces where ordinary matter condenses, but those spaces exist at all only because dark matter holds them together. This realization creates an odd tension. The universe's stability, its capacity to host stars long enough for planets to form, is built on a foundation made of something completely incompatible with biology. Dark matter is, in a sense, the universe's first boundary, and its qualities raise unsettling questions. Although it stabilizes galaxies, dark matter does not behave uniformly everywhere. Simulations and observations suggest that its distribution is clumpy, irregular, woven into a cosmic web. These filaments stretch across immense distances, defining where galaxies can form and where they cannot. Between them lie vast voids where dark matter is sparse and where structure fails to arise. In those voids, nothing gathers. No stars ignite. No planets form. No chemistry evolves. Dark matter's silence becomes a barrier, preventing the accumulation of matter required for life. Even within galaxies, dark matter halos influence the motion of stars, dictating patterns that appear stable only on cosmic timescales. But the stability they create is not gentle. It is imposed by a gravitational presence that neither knows nor cares what life requires. Dark matter's gravitational influence is strong but indifferent. It holds galaxies together, but it also shapes them in ways that sometimes hinder the formation of habitability. Dense regions of dark matter may squeeze gas clouds until they collapse too quickly, igniting stars that burn too bright and too fast. Sparse regions, by contrast, fail to gather enough matter to form stars at all. Life needs a balance, but dark matter's patterns are not drawn with balance in mind. They are drawn by physics older than chemistry, older than stars, physics that predates even the formation of atoms. What dark matter truly is remains unknown. It could be a particle, it could be a field, it could be something stranger, a remnant of an earlier phase of the universe. Whatever its nature, its existence hints that the laws we observe are only part of a deeper structure, one that does not incorporate life into its equations. We evolved in the shadow of a substance that shapes the cosmos but does not acknowledge us. There is another layer of complexity. Dark matter may not be entirely uniform. Some theories suggest it could interact weakly with itself, forming clumps or waves that alter the gravitational environment subtly over time. If true, the distribution of dark matter might shift across epochs, changing the architecture of galaxies in ways that planets and stars cannot anticipate. In regions where dark matter density is too high, stars form rapidly and die violently, flooding their surroundings with radiation. In regions where dark matter density is too low, matter drifts aimlessly, unable to collapse into structures dense enough for life. In both extremes, the quiet corridor required for biology dissolves. Dark matter might also influence the dynamics of solar systems indirectly. Its gravitational presence is subtle but persistent, capable of altering the orbits of stars over cosmic time. If a star's motion shifts too abruptly, its planets may drift from stable orbits, losing their delicate climates. A tiny change in gravitational environment, occurring over millions of years, can be enough to destabilize conditions on the surface of a world. Life cannot adapt to orbital chaos. It requires predictability over vast spans of time, predictability that may be disrupted by forces it can neither sense nor avoid. This introduces a deeper idea. The universe's largest stabilizing force may also be a long-term source of instability. Without dark matter, galaxies fall apart. With too much of it, they collapse too violently. With too little, they drift without forming stars. With uneven distribution, they shift unpredictably over time. Life exists within the narrow band where dark matter contributes just enough structure without overwhelming it. But that narrowness is fragile. Because dark matter is invisible, its behavior is inferred from motion not directly measured. We cannot predict how it moves with certainty. We cannot model its influence on long timescales with precision, and we cannot protect ourselves from changes in its distribution. We live in a cosmos where the dominant form of mass is something we do not understand, cannot interact with, and cannot shield against. Life depends on ordinary matter. Yet ordinary matter floats inside a sea of something else. Something colder, heavier, less responsive, and incomparably more abundant. Biology is a minority presence. Dark matter is the majority, and the majority dictates structure. There is a strange humility in acknowledging this. We are not built into the foundation of the cosmos. We are built into its residue, the 5% of matter that behaves chemically, bonds electrically, radiates thermally, and gives rise to living forms. The other 95% shapes the stage while remaining entirely unreachable. This imbalance also suggests something deeper. If life is rare, it may not be because planets are scarce or because chemistry is difficult. It may be because the fabric of the universe is woven from substances indifferent to complexity. That indifference is not antagonism. It is simply the natural state. Dark matter has no temperature relevant to biology, no charge, no interactions, no chemistry, no presence in the electromagnetic fields that enable DNA, proteins, neurons, and membranes. It provides gravity, the one force life cannot use to build itself. Gravity shapes structure, but it does not assemble complexity. Light can catalyze chemistry. Electricity can drive reactions. Magnetism can organize particles. Nuclear forces can forge elements. Gravity only pulls. It pulls galaxies into existence. It pulls stars into ignition. It pulls planets into orbit. But it pulls too slowly to build life and too steadily to stop. Life must arise in the quiet spaces gravity shapes, but gravity does not care whether those spaces endure. And as you follow that thought, something subtle shifts inside the mind. The realization that life is not written into the deep structure of the universe. It grows only where the deeper structure fails to eliminate the narrow conditions required for it. We live in a cosmos held together by something invisible, something ancient, something structured yet inscrutable, a vast gravitational ocean, whose currents give shape to everything we know, and yet whose depths remain beyond the reach of any living system. In that ocean, life is not the pattern. It is the ripple, a ripple that forms briefly along the surface of a sea that has never known the warmth of being seen, touched, or understood. The thought of being shaped, silently, by something invisible lingers as a quiet weight. Dark matter gives the universe a kind of structure, an unseen spine, but even that structure is temporary. Because layered beneath the gravitational web is another, more subtle presence, a presence not of attraction, but of separation. If dark matter binds, dark energy unbinds. It is the most dominant component of the cosmos, and yet its behavior is opposite in nature to everything life depends on. Life needs gathering, clustering, concentration. Life needs matter to come together in intricate arrangements. But the largest force in the universe works in reverse. It pushes, it stretches, it drives everything away from everything else. Dark energy is not explosive, it is not violent. It is a gentle insistence, accelerating all distances between unbound objects. Its influence is so soft that it went unnoticed for billions of years. Yet, on the scale of galaxies, of cosmic filaments, of the fabric of spacetime itself, its touch becomes unmistakable. Imagine the universe as a vast sheet, once expanding steadily, then beginning to accelerate outward, as if pulled from the edges by an invisible hand. That acceleration, small, smooth, persistent, is the signature of dark energy, and it is rewriting the fate of everything. In the early universe, gravity dominated. Matter clumped, cooled, condensed. Stars formed. Galaxies emerged. Life appeared because the cosmos lingered long enough in this temporary era of balance. But now, the balance is shifting. Dark energy has begun to outweigh the influence of matter, ordinary and dark combined. The universe is entering a new phase. a phase unfriendly to connection. As space expands faster and faster, galaxies drift apart. The light they emit stretches into longer wavelengths, fading into invisibility. Over time, even the nearest clusters will slip beyond reach, not because they move away, but because space-time itself expands between them. Life depends on proximity. Dark energy creates distance. Once you grasp this, the significance becomes clear. The universe is not a static backdrop for existence. It is moving, evolving, changing, and its long-term trajectory is toward increasing isolation. This isolation is not merely aesthetic. It defines the environment in which future life must try to exist. But life cannot thrive in isolation. It needs stars, energy gradients, chemical cycles. All of these require matter to remain concentrated. Yet dark energy works against concentration at every scale beyond the gravitational binding of galaxies. And eventually, even that binding may not be enough. If dark energy strengthens, if its density increases over time, the acceleration will grow so extreme that galaxy clusters will separate, then galaxies themselves, then solar systems, and ultimately, even atoms. This speculative fate is known as the Big Rip, where space-time tears itself apart. Even if dark energy remains constant, its influence ensures a quieter but equally certain future. A future where galaxies become lonely islands in an ever-expanding sea. A future where light disappears from the cosmic horizon. A future where the universe cools into emptiness. In every scenario, the trajectory moves away from life. The story of dark energy begins with an unexpected observation. Distant supernovae were dimmer than they should have been. They weren't dying differently. They were simply farther away than expected because the space between galaxies had stretched more than anticipated. Something was accelerating the expansion. That something now dominates cosmic evolution. Physicists describe dark energy with the cosmological constant, a parameter that defines how quickly space-time expands. But naming it does not illuminate its nature. It could be a property of space itself, a field that permeates everything, or a manifestation of energy stored in the vacuum. It could even be an artifact of deeper physics. We have not yet glimpsed, something tied to dimensions or interactions we cannot detect. Whatever it is, it moves with mathematical certainty, reshaping the universe slowly but relentlessly. Its effect on life is subtle at first. The distances between galaxies increase. The cosmic microwave background cools. The overall density of matter decreases. In the near future, astronomically speaking, this changes nothing about local environments. But life does not exist on short scales. It depends on trillions of years collectively, across generations, across evolutionary arcs. And on those scales, dark energy becomes decisive. As galaxies move apart, fewer new stars form. Gas clouds thin. Heavy elements become rarer. Young worlds that might have nurtured life never appear. The universe grows dimmer, quieter, older. In this expanding loneliness, the conditions that once allowed life become increasingly scarce. In the very far future, star formation ceases. The stars that remain will be small, faint, and slow-burning, stretching their lives over trillions of years. But they will be isolated, surrounded by distances so vast that light itself will no longer bridge them. The cosmos will become uninhabitable, not by violence, but by emptiness. Life can adapt to harshness, radiation, geological upheaval, but it cannot adapt to nothing. It cannot adapt to infinite cold or infinite separation. The systems that sustain biology, energy flow, chemistry, proximity, depend on a universe rich in gradients and interactions. Dark energy dissolves those gradients. Everything becomes evenly spread, uniform. Still, it is the stillness that ends life, not a catastrophe. Yet the story is more complicated. Dark energy shapes the universe not only on cosmic scales, but also through subtle effects that cascade down into the structures where life might arise. The growth of galaxies, the formation of stars, the distribution of heavy elements. All of these depend on the balance between gravity and expansion. If expansion outpaces collapse too early, galaxies would be small and chaotic. Stars would form irregularly, planets would be unstable, chemistry would stall, and indeed, the universe nearly reached that state. The amount of dark energy appears to be precisely what allows galaxies to form, and slightly more would have prevented them from doing so. Slightly less, and the cosmos would have collapsed prematurely. This fine balance deepens the sense of fragility surrounding life, because dark energy, like everything else in the universe, does not tune itself with biology in mind. Its value is not a gift, it is a parameter that emerged from the early universe, indifferent to the consequences. The fact that its current density allows galaxies to exist is a coincidence that enables life briefly, before the same parameter ensures that galaxies eventually fade from each other's sight. If dark matter shapes the universe's bones, dark energy pulls on its skin, and the pull grows. One by one, galaxies drift beyond the cosmic horizon, the limit of what any observer can see or touch. Eventually, only the stars within one gravitational group remain visible. Everything else becomes unreachable, not because it has moved, but because space-time expands faster than light can travel. Isolation becomes absolute. From the perspective of life, this isolation is catastrophic, but not in a single moment. It unfolds gradually, like the dimming of a lantern in a vast room. The corridors of possibility grow narrower, the pathways for evolution shrink, the diversity of environments collapses. The universe becomes a collection of small, fading pockets of heat, surrounded by infinite cold. And within those pockets, life continues its attempt to persist, but the environment works steadily against it. Stars exhaust their fuel, planets cool, chemistry slows. Eventually, even the atoms themselves may decay, though this remains uncertain. The force responsible for this decline is soft, almost gentle. It is not fire. It is not collision. It is not explosion. It is expansion, smooth, continuous, all-reaching. This gentleness is part of what makes dark energy so difficult to grasp. It is the opposite of drama. It is the opposite of violence. It exerts no pressure, delivers no shock, emits no radiation. It cannot be shielded against, because it shapes the geometry of the universe itself. Dark energy is the quiet certainty that everything grows farther apart. And in that increasing separation, the universe reveals another of its boundaries, a boundary not of space, but of connection, a boundary that life cannot cross, because the processes that maintain life depend fundamentally on proximity, on interaction, on energy shared across short distances. As expansion accelerates, the space available for life does not shrink. It becomes irrelevant, because the distances within that space grow faster than life can compensate for. In the stillness that follows this realization, a strange picture forms. Life does not end because something destroys it. It ends because the universe behaves in a way that sustains its own structure, not the structures that life needs. A structure defined by geometry, by expansion, by distances increasing without limit. It is in this widening silence that one begins to understand how deeply the universe moves according to rhythms that do not include us. These rhythms do not oppose life. They simply do not bend for it. They continue, undisturbed, shaping a cosmos where complexity is allowed only briefly. In the rare moments when the accelerating drift has not yet pulled everything beyond reach. And in those moments, life arises, a fragile arrangement of matter, shining quietly against a backdrop that is already pulling itself apart. As soon as you begin to understand how dark energy stretches the universe outward, something else becomes clear. Not all regions drift into emptiness. Some collapse so violently, so completely, that matter no longer behaves as matter. These places do not simply resist life. They undo the very forms on which life depends. They are the densest, darkest objects the universe can make. Not through decay, but through concentration, where dark energy pulls the cosmos apart. These objects pull inward with such intensity that the rules of space and time reorganize themselves around the collapse. Black holes, neutron stars. They are the opposite of the quiet expansion that defines the universe's future. They are the extremes of its past, frozen remnants of catastrophic endings, born from the deaths of massive stars. Yet they do not feel like corpses. They feel like boundaries. Boundaries not meant to be crossed, not meant to be approached, and certainly never meant to contain anything living. To understand them, begin with a star much larger than the sun. A giant burning with a brightness that shortens its own lifespan. It exhausts its fuel quickly, collapses inward, under its own gravity, and detonates. In a supernova, most of its mass is blasted away. But the core remains, crushed by pressures unimaginable. What happens next depends on the mass that survives. If the core is heavy enough, electrons and protons are squeezed into neutrons. The result is a neutron star, a sphere barely tens of kilometers across, yet heavier than the Sunday. Its surface gravity is so intense that the difference in height between your head and your feet would tear you apart. The atoms inside it no longer contain empty space. They exist as a single, dense sea of neutrons packed to their theoretical limits. This is matter pushed to the edge of possibility. And yet, neutron stars behave in ways even stranger than their density suggests. Many spin hundreds of times per second rotations so fast that they drag magnetic fields into structures more powerful than anything else known. These magnetic fields channel beams of radiation that sweep across space like cosmic lighthouses. But these are not gentle beams. They are pulses of high-energy photons and particles that sterilize everything in their path. Life cannot survive near a neutron star. Nor can chemistry. Nor can atoms, if they drift too close. Everything is stripped, shredded, or altered into forms unrecognizable. But the neutron star is still only the threshold. If the collapsing core exceeds a slightly larger mass, even neutrons cannot withstand the pressure. The collapse continues inward, unstoppable, until density becomes infinite. Space folds, time slows. A boundary forms the event horizon beyond which nothing, not even light, can escape. A black hole is not a thing. It is an absence, a region where the known rules of physics stop yielding answers. Approach it, and you do not simply fall. You are stretched by tidal forces that grow stronger with every meter. Atoms are elongated, molecules unwind. Even the structure of spacetime begins to distort under your feet. But perhaps the strangest feature of a black hole is not how it destroys matter, but how it isolates information. Once something crosses the event horizon, its details, the patterns that define its structure, are lost to the observable universe. They are not destroyed exactly, but encoded on the horizon itself, inaccessible, unreachable, removed from the continuity that life requires. Life needs continuity. Black holes sever it. Yet black holes are not rare. There is one at the center of every large galaxy, including our own, a supermassive object millions of times heavier than the Sunday stars orbit it. Gas falls toward it. Entire clusters of worlds drift under its gravitational influence. In the early universe, these giants shaped the growth of galaxies, controlling star formation through jets that span thousands of light years. These jets are made not of light but of matter ripped apart, accelerated to near-light speed, and fired into space in beams so powerful they sterilize regions far beyond the black hole itself. They do not create. They prevent creation. If a young galaxy experiences too much activity from its central black hole, star formation halts. Gas is heated, scattered, or expelled. The raw material for life is denied. The galaxy becomes a silent shell, glowing faintly but offering no new opportunities for biology. Even small black holes threaten habitability. A wandering black hole passing through a star-forming region can distort orbits, strip matter from gas clouds, or disrupt the gravitational harmony needed for planets to form. It is unlikely to happen, but the possibility exists, hidden in the vastness of time. Black holes shape galaxies not only through destruction, but also through their gravitational presence. They anchor stellar orbits, influence the clustering of matter, and dictate the pathways by which galaxies merge. During galactic collisions, the central black holes spiral toward each other, emitting gravitational waves ripples in spacetime that stretch and compress the universe itself. These waves pass through everything, including worlds, though too faintly for life to notice. Yet the mergers that produce them release energies so extreme that entire regions of the galaxy may be disrupted. And through all of this, black holes remain completely indifferent. They do not radiate malice. They simply follow gravity to its ultimate conclusion. Between black holes and neutron stars lie other hazards. Magnetars, the most magnetic objects in existence, can emit bursts so powerful they affect planets thousands of light years away. Pulsars rotate with such precision that their beams behave like cosmic clockwork. Some emit enough energy in a single second to power human civilization for millions of years. These phenomena are mesmerizing from afar, but they erase the conditions life needs to begin. The deeper truth is this: the universe forms extreme objects more easily than it forms habitable worlds. Massive stars collapse into neutron stars or black holes in just a few million years an instant compared to the billions required for complex life. Stellar nurseries produce far more violent stars than gentle ones. Gravity tends toward extremes. Matter tends toward collapse. Energy tends toward release in forms biology cannot survive. In a very real sense, the universe's default mode is to build monsters long before it builds homes. Homes are the exception. Even the quiet emptiness between stars, which seems peaceful compared to these extremes, is shaped by their influence. Shockwaves from supernovae propagate for thousands of years, seeding regions with heavy elements but also clearing out pockets of gas where planets might have formed. The balance between nourishment and destruction is delicate and always leaning toward destruction. Life requires conditions that rarely exist anywhere near these objects, and yet, these objects dominate the galaxy's evolution. They are part of the cosmic ecosystem in a role opposite to life. They prune, limit, and constrain the environments where complexity can grow. But there is one more layer to their story, one that deepens the strangeness of their presence. The existence of black holes hints that our understanding of physics is incomplete. Information appears to be trapped. Space and time behave unpredictably. Quantum mechanics and general relativity collide without reconciliation. Black holes are not only hazards to life, they are boundaries of knowledge. They represent the edges of what the universe lets us understand. Life, in contrast, depends on predictability, on rules that can be followed, on patterns that remain stable long enough for cells to divide, evolve, and reflect. Where the rules break, life cannot follow. As stars die and collapse into these extreme forms, they leave behind zones where matter forgets the shapes it once held, where energy behaves without reference to chemistry, where the familiar scaffolding that life requires dissolves into curvature and pressure and silence. It is in the presence of these objects that the universe reveals its deeper nature, not as a cradle, but as a continuum of processes that rarely intersect with life's needs. Processes that build marvels, but not havens. Processes that create wonders, but not the conditions for breathing. And in the spaces between these extremes, somewhere far from the crushing gravity and erasing light, life momentarily gathers itself quietly, carefully before the universe's larger forces pull it back into the fold of their indifferent motion. There is something unsettling that begins to rise once you've walked through the extremes, the violent compression of neutron stars, the erasing silence of black holes, the collapsing and stretching of space-time itself. A deeper question presses upward, like a slow tide. Why does the universe produce so many environments that deny life, yet so few that permit it? It is tempting to search for intention, but what emerges instead is a different suspicion. The suspicion that our understanding of the laws themselves is incomplete. That the universe behaves in ways we are not equipped to interpret, because the frameworks we use to describe it were never designed to explain everything. There are fractures in our knowledge, subtle at first, but widening as we look more closely. Gravity, the force shaping galaxies and collapsing stars, is described by general relativity, a theory of enormous beauty and precision. It explains how mass curves spacetime, how orbiting bodies fall along that curvature, how clocks tick differently in different gravitational fields. But on the smallest scales, where particles dance, where fields fluctuate, where life emerges, general relativity fails. It cannot describe atoms. It cannot explain the structure of matter. It cannot merge with the quantum laws that govern everything close to life's architecture. Quantum mechanics, on the other hand, describes the microscopic world with astonishing accuracy. It reveals a universe filled with probabilities, fluctuations, virtual particles, tunneling events, constant change beneath the surface of stability. But it cannot describe gravity, and gravity shapes the universe at every scale larger than a molecule. These two frameworks, each brilliant, each successful, refuse to speak the same language. This is the first point where our understanding fractures. Life exists precisely at the intersection of these regimes. Too small to ignore quantum effects, too large to escape gravity's influence. Yet the theories that describe these realms do not yet merge. Between them lies a gap, a place where the rules we rely on lose their coherence. And in that gap may reside an explanation for why the universe feels so unconcerned with life. Because if the laws are incomplete, then their apparent indifference may not be a property of nature, but a property of our models, a misunderstanding, a misalignment, a lens not ground finely enough to see what is truly there. Still, this incompleteness does not comfort. It complicates. Consider the vacuum of space, the emptiness that fills nearly all of the universe. In classical physics, empty space is simply nothing. But quantum physics reveals something stranger. The vacuum is a seething field of energy. Virtual particles appear and vanish continuously. Forces emerge not from objects, but from the fluctuations in this invisible sea. Yet, general relativity interprets vacuum energy as something entirely different, a source of spacetime curvature, a pressure that accelerates the expansion of the universe. These two interpretations collide. Quantum theory predicts an enormous vacuum energy far larger than anything observed. General relativity demands a value 120 orders of magnitude smaller. This is not a minor discrepancy. It is the largest mismatch between theory and observation in the history of science. And it matters deeply for life. Because vacuum energy, if it were even slightly different, would either tear the universe apart before matter could gather, or collapse it before atoms could form. The fact that vacuum energy has the value it does is one of the greatest puzzles in physics. A puzzle with biological consequences. A puzzle that shapes the boundaries of existence. Why does the universe permit life at all? Why is vacuum energy so precisely tuned? Why do the constants sit at values that allow stars, chemistry, and time? Some argue coincidence. Others argue selection. But the truth is, we do not know. This uncertainty becomes more profound when you examine the structure of spacetime near a black hole. There, the predictions of relativity break down completely. Singularities arise points of infinite curvature. Quantum corrections are needed, but no quantum theory of gravity exists. In these regions, our equations fail, and where they fail, we cannot describe what is real. We can only approximate. Perhaps the universe contains phases of matter or energy that we do not recognize. Perhaps the constants we measure are local, not universal. Perhaps the laws are emergent, not fundamental. These are not fringe ideas, they are serious possibilities, proposed by physicists trying to reconcile the cracks in our understanding. The unsettling possibility is that the universe's apparent hostility to life may originate not from the universe itself, but from the shape of our ignorance. Maybe life is not rare. Maybe our models simply cannot detect the conditions that make it possible elsewhere. Or perhaps the opposite is true. Life is rare because the laws we have discovered are merely a surface, and beneath that surface lies a deeper architecture built for purposes that have nothing to do with biology. Either way, the gap in our knowledge is not merely academic. It shapes how we interpret the universe's behavior. Consider the cosmological constant again. It is small, but not zero. It accelerates expansion, but barely. It provides structure early on, then erases structure later. It feels almost contradictory, as if it plays multiple roles. Some theories propose that the constant is not constant at all, that it evolves through quantum fluctuations. If so, then the entire trajectory of the universe's hostility to life could shift over time. Conditions that once favored stability could drift into instability. Habitable worlds could become uninhabitable not because their stars evolve, but because the fabric of space-time itself slowly changes. Other theories propose extra dimensions curled into shapes too small to see. These dimensions could influence the constants we observe. They could shift subtly over cosmic time. They could destabilize the narrow window where life thrives. If dimensions can shift, conditions can drift. And if conditions drift, life's foothold narrows further. Then there is the possibility that the observable universe is only one region within a larger multiverse, each region with different constants. If that is true, then our universe is not hostile, it is simply one of countless configurations, and most of those configurations cannot support life. Our existence becomes the result of selection, not design. But this idea raises another question. If life is an outcome only in specific regions, why does our region appear balanced so precariously? Why is the line between possibility and impossibility so thin? Perhaps the laws themselves are unstable, frozen now, but subject to transitions. Perhaps they can shift suddenly, as they did in the early universe, changing the rules midstream. A slight shift in the vacuum state could erase atoms, collapse chemistry, or alter nuclear reactions. Life would vanish instantly, without warning, without violence. Not because the universe turned hostile, but because the rules changed. In this context, the apparent hostility of the universe becomes not a deliberate property, but a side effect of rules that are incomplete, evolving, or misunderstood. Our models describe the universe well enough for us to survive within it, but not well enough to know whether the universe is stable beneath our feet. The more closely we examine the foundations, the less solid they appear. Not because they are weak, but because they are deeper than our tools can reach. Life exists in the realm of approximations. The universe exists in the realm of absolutes. And the gap between those realms grows wider the more we learn. It is in this widening gap that the unease returns, the sense that life is not merely rare, but contingent on aspects of reality we do not fully grasp. And because we do not grasp them, we cannot trust the stability of the conditions that permit us. Yet there is also a strange calm in this uncertainty, a recognition that the universe's indifference may not be personal. It may simply be the echo of deeper rules, still hidden, unfolding according to principles that do not yet have names. Life waits inside those unnamed principles, aware of how little it understands, yet continuing anyway, held together by patterns that persist just long enough to feel like meaning, even in a universe whose deeper foundations remain beyond reach. There comes a moment, after tracing the fractures in our understanding, the mismatch between gravity and quantum mechanics, the mystery of vacuum energy, the strange precision of the constants, when a new thought begins to take shape. It does not shout. It does not arrive like revelation. It simply settles, with the quiet certainty of something that has been waiting for a long time. Maybe the universe is not indifferent because it is cold. Maybe it is not hostile because it is extreme. Maybe it is not mysterious because we have not studied it long enough. Maybe it is indifferent because life was never part of its purpose, not rejected, not excluded, just never considered. When you look at the universe through this lens, everything rearranges itself in subtle ways. The violence of supernovae no longer appears intentional. The scarcity of habitable worlds no longer feels personal. The thin corridors where biology can exist become not invitations, but oversights, small gaps in a machine designed to do something else. This idea sounds unsettling at first, as if it steals significance from everything alive. But in truth, it clarifies something important. The universe is consistent. It behaves the same everywhere, without preference or exception. The conditions that permit life are rare, not because the universe resists life, but because the universe follows rules that do not include life in their equations. Life arises in the same way crystals form in cooling rock, or bubbles appear in boiling water, not as an intention, but as a consequence. The idea becomes clearer when you study the evolution of matter itself. In the earliest fractions of a second, the universe expanded, cooled, and separated into forces that still govern everything. Nothing about these transitions favored biology. They favored stability, predictability, mathematical coherence. Life requires oxygen, carbon, liquid water, complex molecules, but the universe requires none of these. It requires symmetry. It requires balance. It requires the conservation of energy and momentum. It requires the existence of fields that break in specific patterns. Life is not written into these requirements. It is written into the margins. Look at the formation of atoms. They appeared not because the universe desired chemistry, but because protons and electrons behaved in ways that allowed stable relationships under certain temperatures. Most combinations failed. The few that succeeded produced hydrogen, helium, and traces of lithium, simple ingredients that later fused into heavier elements inside stars. Stars did not ignite to create biology. They ignited because gravity compressed gas until nuclear reactions became unavoidable. Planets did not form to host oceans. They formed as accidental aggregates, leftover debris swirling around young stars. Water did not gather to nurture life. It gathered because oxygen and hydrogen happened to bond in a way that remained stable across a wide temperature range. Life used these conditions, but the conditions were not made for life. Once this perspective sinks in, a strange harmony reveals itself. Life does not need the universe to intend anything. It needs only the absence of barriers, and even that is temporary. The more you examine biological evolution, the more this becomes evident. Life does not appear immediately. It appears after billions of years of chemistry pushing against probability. It arises in environments that have already stabilized enough to shield against destruction, but not so stable that chemistry stops experimenting. The universe does not foster these environments. It simply fails, in a few places, to prevent them. Imagine a cosmic landscape governed by equations, seeking balance between forces, between expansion and collapse, between energy and geometry. These equations are not fine-tuned for life. They are fine-tuned for consistency. Life appears only where consistency produces complexity by coincidence. This is not cynicism, it is clarity. Even the constants often cited as fine-tuned for life look different under this light. The strong nuclear force is not tuned so that carbon can exist. It is tuned so that atomic nuclei can exist at all. The cosmological constant is not tuned to allow galaxies. It is tuned to prevent runaway curvature. The electron charge is not tuned for chemistry. It is tuned for stable electromagnetic fields. Life fits into these values by accident. The values were never meant to fit life. This framework also aligns with something deeply mathematical. Most possible universes, if any could exist, would not permit complexity. Not because complexity is discouraged, but because complexity requires extremely precise balances. These balances are not typical. They are improbable. They are rare outcomes on the landscape of physical possibility. Life is not the goal of these outcomes. It is a passenger. And yet, when biology appears, it behaves as though it belongs here, branching into forests, rising into consciousness, sculpting meaning out of noise. Life acts with intention in a universe that has none. This mismatch, the intentionality of organisms within the non-intentionality of the cosmos, creates a tension that underlies every existential question ever asked. It is the tension between purpose and physics. Life feels purposeful because it acts with direction, survival, replication, adaptation, curiosity. But physics does not act. It simply unfolds. It produces stars, not because they are needed, but because gravitational collapse leads inevitably to ignition. Under this view, the hostility of the universe is not hostility at all. It is neutrality. Neutrality so vast and so consistent that it feels like opposition because life is fragile. Yet fragility does not imply mistake. It implies the opposite: resilience against a backdrop that never bends. Even intelligence, something rare enough that we have not confirmed its existence elsewhere, emerges not because the universe aims to understand itself, but because evolutionary processes occasionally favor complex cognition. Intelligence is an adaptation, not a destination. the universe would proceed identically without it. This realization reframes the question entirely. Instead of asking why the universe appears unfriendly, we must ask why we projected friendliness onto it at all. Perhaps because living things are surrounded, from birth, by environments that feel designed for survival: air, warmth, food, water. Perhaps because every organism experiences intention at the local scale, in the form of parents, patterns, cycles. But the universe is not local. It is vast, and its rules operate far beyond anything biological. Biology is structured around gradients, energy flowing from high to low, chemistry building order from disorder, systems maintaining themselves against entropy. The universe is structured around entropy itself, the gradual diffusion of everything, the cooling of everything, the drift toward uniformity. Life is a contradiction carved into that trend, a temporary reversal. Eventually, the trend wins, not because it opposes life, because it does not recognize life. Still, there is an odd comfort hiding inside this dispassionate cosmology. If the universe did not intend life, then life does not owe the universe obedience or gratitude. Life is free to define itself, free to create meaning, free to build structures that do not exist anywhere else, free to pursue patterns that physics alone cannot generate. In a universe without intention, intention becomes precious. In a universe without purpose, purpose becomes self-created. In a universe without design, design becomes an act of defiance. This, too, reframes fragility. Life is not fragile because the universe forbids it. Life is fragile because it is built from processes that delicately borrow stability from a system that does not specialize in stability. But fragility does not deny significance. Often, it deepens it. There is something undeniably profound about a universe that creates complexity unintentionally. Complexity that then turns around and notices the universe itself. Awareness becomes an emergent property of coincidence. Consciousness becomes the echo of accidents aligned just right. Meaning becomes something generated from within, not granted from without. And in that echo, life discovers something quietly liberating. It was never meant to be here, yet it is here anyway. A brief, luminous interruption in a reality shaped by rules that flow endlessly past it, unaware, unchanged, untouched. Once you accept the possibility that the universe never meant to create life, another idea steps forward quietly, almost apologetically, as if aware of its weight. If the cosmos did not aim for life, then life itself must be a statistical outlier, a rare fluctuation among billions of non-fluctuating possibilities. Not rare in the poetic sense, rare in the mathematical sense, rare in a way that resists intuition. Probability becomes the language here, not the probability of a species forming or a civilization rising, but the probability of chemistry combining into something capable of persistence against entropy. When you examine the history of the universe through this lens, it begins to look like a long series of unlikely events occurring inside an even longer series of indifferent processes. Matter forms unlikely. Atoms stabilize unlikely. Stars produce heavier elements without destroying everything unlikely. Planets survive their formation unlikely. Habitability lasts long enough for chemistry to continue unlikely. Self-replicating molecules appear extraordinarily unlikely. Those molecules resist degradation more unlikely still. And from that chain of improbability emerges something that calls itself alive. Each step is a narrowing of possibilities, a reduction of outcomes, a move towards something that has no guaranteed place in the architecture of physics. It is tempting to think life should be widespread simply because the universe is vast. But size does not compensate for improbable pathways. If a process is unlikely at every stage, expanding the number of trials does not guarantee success, it merely increases the number of failures. Consider the chemistry behind life. All living organisms depend on long-chain molecules, RNA, DNA, proteins, constructed from smaller building blocks. But these structures form only in environments where energy gradients are precise, temperatures are moderated, and solvents behave with unusual stability. Most environments fail at one of these requirements. Many fail at all of them. Even water, often considered essential to life, is peculiar. It remains liquid across a narrow temperature range. It expands when it freezes, an anomaly among liquids. It moderates heat with extraordinary efficiency. If water behaved slightly differently, life's existence would be improbable enough to vanish entirely from the realm of possibility. And water is not universal. Even on planets that possess it, the window in which it remains liquid is often brief. Biology requires more than presence. It requires persistence. This dependence on persistence is what makes life so improbable. Chemical reactions occur everywhere, but they rarely reinforce themselves. Most reactions dissolve into equilibrium, stable, unchanging, lifeless. To escape equilibrium, a system must maintain a flow of usable energy, a cycle of building and breaking that continues long enough for complexity to accumulate. Such cycles are rare. They require an environment neither too violent nor too quiet. They require sources of energy neither too strong nor too absent. They require protection from destabilizing events. And even then, the molecules must resist the constant pull of entropy. Life is not a spark. It is a sustained defiance. But defiance is not expected. It is not common. It is not favored. When scientists model prebiotic chemistry, they find that self-replicating molecules are not inevitable. They are one success hidden among mountains of failure. Most chemical networks collapse or drift into randomness before coherence emerges. If you treat the emergence of life as a combinatorial problem, the odds shrink with every variable. If you treat it as a thermodynamic problem, the odds shrink further. If you treat it as a probabilistic event within cosmic evolution, the odds shrink beyond comprehension. Probability does not care about desire. It does not adjust itself for observers. It flows according to the arithmetic of outcomes. And by that arithmetic, life is not a default. It is a deviation. Yet deviations matter, especially when they persist long enough to notice themselves. Life is a pattern that survives. But survival requires a sequence of luck at almost every step. Not just luck in chemical formation, but luck in environmental timing. The Earth itself demonstrates this fragility. It formed in a region with the right mixture of heavy elements, but that mixture was the product of countless supernovae. Had one explosion been slightly stronger or slightly closer, the material forming Earth might have been blown apart. Later, Earth's orbit stabilized in a narrow band of temperatures, but this stability depends on gravitational interactions with the Moon and Jupiter. A subtle shift in the early solar system could have altered every climate cycle. Even after life began, it did not flourish immediately. Earth remained dominated by simple organisms for billions of years. Multicellular life was a late accident. Intelligence, even later. Civilization, later still. The waiting period for complexity is immense. The tolerance for disruption is thin. This asymmetry between how long life takes to evolve and how short stability tends to last suggests that most worlds never reach complexity. Many may begin the process, only to be interrupted by impacts, flares, glaciations, or internal geological failures. Unlikelihood is not measured only by origin, but by longevity. Survival is a statistical anomaly, and yet, here life is observing its own improbability. This raises another question. If life is so unlikely, why does it feel natural once it appears? The answer lies in a cognitive bias built into biology. Living things experience the world from within structures that succeeded. Every organism carries the false impression that life is typical because it is surrounded by life. The success of living systems hides the innumerable failures that prevented other paths from continuing. This is not a mistake. It is a perspective. Life sees only the environments in which life survived. It cannot see the vastly larger number of places where life did not. The night sky holds no record of failures. It holds only silence. And in that silence is the evidence of how improbable life truly is. Probability also shapes evolution. Random mutations produce variations, but most variations do not improve survival. Evolution proceeds not by inevitability, but by filtering through chance events, asteroid impacts, climate shifts, Ecological openings. Had one extinction event not occurred, mammals might never have risen. Had one continent drifted differently, ecosystems would not resemble what they do. Had one genetic pathway failed, intelligence might never have formed. The world we inhabit is one version of many unrealized possibilities. This does not make life meaningless. It makes it fragile, and fragility is the source of its significance. If life were inevitable, it would be ordinary. If consciousness were guaranteed, it would be unremarkable. If complexity arose everywhere, it would not feel extraordinary to emerge within it. Rarity gives weight. Improbability gives depth. A statistical accident still produces beauty when it persists. And perhaps the most humbling part of this entire picture is that the universe neither notices nor resists these accidents. It allows them in the same way it allows storms, or stars, or crystals briefly, locally, without preference. Life flows through the cracks of probability, not because the universe makes room for it, but because the universe is too vast and too intricate to prevent every unlikely thing from happening somewhere. Life is the residue of that openness, a byproduct of a system that does not specialize in it, yet does not forbid it. In this sense, life is not an impossibility. It is an inevitability not everywhere, but somewhere, not common, but guaranteed by sheer scale. Scale outweighs improbability, but scale does not soften reality. Every instance of life remains a statistical triumph against overwhelming odds. And in recognizing this, something shifts. You begin to see life not as a central feature of the universe, but as a luminous exception, a fragile interruption, in a cosmos that otherwise follows its own equations, drifting unconcerned through outcomes where life is not only absent, but unnecessary. If life is a statistical accident, a rare success hidden among vast fields of failure, then the next realization follows naturally, quietly, almost inevitably. The universe does not merely ignore life, it selects against it, not with intention, not with malice, but through the silent arithmetic of its own laws. In every process the universe performs, from the smallest quantum interactions to the largest cosmic evolutions, there is an unmistakable trend. Simple states dominate, stable structures collapse, order dissolves, and complexity is the exception that requires constant defense. This tendency is not philosophical, it is physical. Life, in this view, is not simply improbable, it is disfavored. It emerges only where the universe momentarily fails to enforce simplicity. These moments, these narrow openings, are carved out by balances so fragile they border on impossible. Consider planetary systems. Their formation is messy. Dust and gas collide. Fragments merge and shatter. Planets drift inward, fall into stars, or are ejected entirely from their systems. Most early worlds do not survive long enough to cool, let alone harbor oceans or atmospheres. Only a fraction stabilize. Only a fraction of those remain stable. The universe produces far more dead, barren, chaotic worlds than living ones. Not because it prefers them, but because simplicity is the natural equilibrium. A planet without life requires no maintenance. A lifeless world is stable. It does not need to regulate temperature, circulate chemicals, or resist biological collapse. Life needs all of that. And still, the universe offers none of it by default. Look at stellar evolution. Stars form from collapsing gas clouds, an inherently unstable process governed by turbulence and randomness. Most stars flare excessively during their youth, sterilizing any nearby worlds. Many stars are too massive and burn too quickly for life to begin. Others are too small and too volatile. Binary stars tug their planets into unpredictable orbits. Rogue stars pass close enough to pull systems apart. The conditions that nurture biology are the least common outcomes of stellar formation. This is anti-selection at the cosmic scale. The universe naturally drifts toward states where life cannot persist. On galactic scales, the trend continues. Supernovae sweep through star-forming regions, destroying worlds before they have a chance to become stable. Dense clusters expose planets to radiation. Galaxy mergers scramble the orbits of stars. Black holes fling material outward or swallow it entirely. Galaxies thrive on the death and rebirth of stars, not on the quiet stability that life requires. Even on Earth, the rare place where conditions settled long enough for biology to flourish, anti-selection is visible everywhere. Meteor impacts reset evolutionary progress. Volcanic winters choke out sunlight. Supervolcanoes destabilize climate. Ice ages advance and retreat. Mass extinction events collapse ecosystems. These processes are not anomalies. They are Earth's normal behavior. Life persists here, not because Earth is stable, but because life has been extraordinarily resilient, rebuilding itself repeatedly after each collapse. Anti-selection shapes evolution itself. Most species do not adapt successfully. Most lineages die out. Most experiments fail. Complexity emerges only when environments remain stable enough, and only for long enough, for evolution to accumulate small innovations. Interruptions, whether cosmic or geological, erase countless branches of possibility. Even the rise of humanity required a sequence of events so specific that changing one variable would erase the entire future of intelligence. This tendency toward collapse is also evident in physics. Entropy increases. Structures decay. Particles fall apart over cosmic timescales. Energy gradients flatten. Systems drift toward uniformity. Complexity is a fight against equilibrium. Life is a brief resistance to the most fundamental trend in the universe. Every time chemistry builds something intricate, thermodynamics pushes back. Every time order increases, entropy whispers it away. Every time life deepens its roots, the universe sends storms, literal and metaphorical, to test the strength of those roots. Anti-selection is not a force. It is the default state. Imagine a river. Its water flows downhill. Life is like a leaf trying to float upstream, not impossible, but requiring constant motion, constant correction, constant effort, and the river never stops flowing. In this metaphor, the universe is the slope. Time is the riverbed. Entropy is the current. Life is the improbable pattern carved against the flow. The deeper you explore biological processes, the clearer this becomes. Cells repair constantly because damage is constant. DNA mutates. Proteins misfold. Membranes leak. Organisms die. Entire ecosystems collapse under minor shifts in climate or chemical composition. Life does not persist because the universe supports it. Life persists because it adapts faster than the background tries to erase it. But adaptation has limits. There are thresholds where complexity collapses too quickly to rebuild. Thresholds where the environment shifts faster than evolution can respond. Thresholds where anti-selection overwhelms the fragile momentum of life. The universe is filled with such thresholds. Solar flares that exceed atmospheric shielding, gamma-ray bursts from distant galaxies, gravitational perturbations that destabilize orbits, dark energy increasing separation between galactic nurseries, black holes consuming star-forming gas, quantum fluctuations in the vacuum, chaotic shifts in climate cycles, plate tectonics running too fast or too slow, chemical pathways that fail to remain stable, planets cooling too quickly, stars heating too slowly, time running out before complexity can emerge. At every scale, the probabilities lean towards simplicity. Anti-selection is not a mechanism. It is a mathematical truth. There are more ways for a system to be simple than complex, more ways to fail than succeed, more routes to collapse than to flourish. Structure narrows possibility. Life narrows possibility further. Consciousness narrows it further still. We live at the very tip of a narrowing spear of improbability. The remarkable part is not that the universe prefers simplicity, of course it does. Simplicity is abundant. Simplicity is stable. Simplicity has no moving parts to break. The remarkable part is that complexity arises at all, that life emerges at all, that intelligence forms even once, anywhere, in a cosmos filled with mechanisms that constantly reset the board. Anti-selection also recasts the story of evolution. Species do not thrive because they are meant to. They thrive because they navigate an environment where collapse is the norm. They succeed not by inevitability but by navigating probabilities stacked overwhelmingly against them. Anti-selection is not pessimistic. It is realistic. It recognizes that life is not the universe's goal, it is the universe's accident. And yet, in this accident lies something extraordinary. Life defies the trend. Life forms patterns that resist dissolution. Life builds systems that reduce entropy locally. Life creates internal order in a universe drifting toward external disorder. The universe favors simplicity, but life refuses to be simple. It grows complexity where no complexity is required. It generates meaning where no meaning is offered. It constructs memory in a world that forgets everything. Anti-selection does not prevent life. It only makes life precious. Because against the overwhelming weight of collapse and decay, life rises not just once, but repeatedly, in every niche that momentarily softens the rules enough to allow it. It rises not as the dominant outcome, but as a luminous deviation from the patterns the universe finds most natural. If the universe tends toward simplicity and life must struggle against that drift, then another realization emerges, one even softer, even more difficult to articulate. The laws of physics are not aimed at life, but the consequences of those laws resemble something that, if seen from a distance, might be mistaken for hostility, not because the universe wishes harm, not because it prefers lifelessness, but because the rules it follows generate conditions that injure the fragile without notice, without pause, without differentiation. The universe does not target life, but life is constantly caught beneath its turning gears. To understand this idea, imagine the foundational laws themselves. Gravity, electromagnetism, nuclear forces, thermodynamics, not as intentions, but as simple patterns unfolding across time. They create stars, but they also destroy them. They allow atoms to form, but they also dissolve them. They let planets cool, but they also let them freeze. They produce water, but they also pull it into steam under too much sunlight. Life fits awkwardly inside these patterns, as though it emerged in a room where nothing was arranged for it, where every corner contains an unintended threat. You can see this clearly in the behavior of entropy. Entropy does not want disorder, but its mathematics ensures that disorder grows. And because life is built from intricate arrangements, chemical, structural, informational, this natural drift toward dissolution acts, inadvertently, as a constant pressure against biology. Cells must repair themselves continuously. DNA must correct errors. Proteins must refold. Membranes must heal. Organisms must metabolize. Species must adapt. In a universe with different laws, perhaps complexity would not require such relentless maintenance. But in this universe, stability decays simply because time moves forward. This decay is not malicious, yet its effect on life is indistinguishable from harm. The same can be said of radiation. Stars shine because fusion releases energy. That energy spreads outward as light. That light, when intense enough, damages molecules, breaks bonds, mutates DNA, destroys cells. Light illuminates, and light erases. There is no intention in this duality. It is the unavoidable consequence of two facts: that nuclear reactions release photons, and that biological structures are delicate. The universe is not aiming its radiance at life. Life simply drifts into paths where radiance is too sharp. This accidental harm appears again in gravity. Gravity organizes matter on large scales, allowing galaxies, stars, and planets to exist. Without it, the universe would be a diffuse cloud. But gravity also creates collapse, crushing cores into neutron stars, pulling atoms past their breaking point, forming black holes that unravel information. Life needs gravity to keep planets together. Yet that same gravity, magnified, creates environments that annihilate it instantly. Physics is full of these dualities. Pressure allows atmospheres. Pressure also kills. Heat allows chemistry. Heat also sterilizes. Cold preserves molecules. Cold also freezes biology into immobility. Magnetic fields shield planets. Magnetic storms strip atmospheres. Water sustains cells. Water dissolves structures if unregulated. These contradictions do not arise from intention. They arise from laws that prioritize coherence over comfort. And coherence is indifferent to living things. On geological scales, these consequences feel almost personal. Tectonic plates move because heat must escape from planetary interiors. Volcanoes erupt because pressure must release. Earthquakes occur because faults must adjust. Climate fluctuates because orbital cycles shift. Each of these processes is fundamental to the planet's long-term stability. Each also threatens life repeatedly. Entire species vanish simply because the planet breathes too deeply or too abruptly. Yet the planet does not breathe with awareness. The cycles unfold because energy must distribute, because materials must move, because the laws allow no stillness. The harm is incidental, the outcome is decisive. Even on biological scales, the universe's rules show the same dual nature. Mutation drives evolution. Mutation also causes cancer. Energy powers metabolism. Energy also produces reactive byproducts that damage cells. Sunlight enables photosynthesis. Sunlight also burns. Mechanisms that nurture life are inseparable from mechanisms that burden it. The line between creation and destruction is thin not by design, but by the nature of the processes themselves. This blending of benefit and harm becomes most vivid when examining chemistry. Carbon forms more diverse bonds than any other element. This versatility allows life to exist. But carbon's flexibility also creates instability structures that degrade, reactions that misfire, pathways that collapse. Life must constantly remake itself because its foundation is inherently unstable. Again, the harm is not intentional. It is an unavoidable side effect of the freedom carbon provides. The same is true of oxygen. Oxygen allows efficient metabolism. Oxygen also corrodes, oxidizes, and degrades organic molecules. Breathing and decay are siblings. No force in the universe seems to act with the intention of harming, yet every force harms as a matter of course. This pattern scales upward through cosmic history. Supernovae forge heavy elements needed for life: carbon, nitrogen, oxygen, phosphorus, iron. But supernovae also sterilize regions of space, blast atmospheres away, and destabilize planetary systems. Galactic collisions mix materials for new stars and planets. They also scorch their centers with radiation and gravitational chaos. Even time itself heals and erodes in equal measure. Long stretches of stability allow evolution. Long stretches also accumulate genetic errors, geological shifts, and cosmic drift. Nothing in the universe stabilizes without destabilizing something else. Perhaps the clearest demonstration of this paradox lies in water, the substance life depends on so completely. Water transports nutrients. Water regulates temperature. Water supports cellular processes. Yet water also dissolves tissues, distorts proteins, and accelerates entropy. Cells must build barriers to keep water both contained and controlled. Too little water kills. Too much kills. Even the perfect solvent is perfectly dangerous. This is the universe's hallmark. Neutral processes, producing harmful outcomes for fragile systems. Yet there is something more subtle here, something that reveals a deeper truth. The rules of physics do not aim to harm. They aim to remain consistent. The harm is a side effect of consistency. Laws that hold everywhere, without exception, produce environments that rarely align with the needs of biological systems, which require exceptions, narrow pockets of stability, localized gradients, temporary balances. Life thrives only in the cracks, where consistency leaves room for complexity. Where consistency is strongest, life cannot exist. Where consistency wavers slightly, life emerges. Where consistency breaks entirely, life is erased. It is a delicate dependency, like a hand resting lightly on a spinning wheel, surviving only because the wheel's rotation is not perfectly smooth. Life is balanced on imperfections. This raises a deeper reflection. Maybe the universe does not harm life unintentionally. Maybe life interprets harm simply because it is built on such fragile foundations that anything not specifically tailored to its survival feels like opposition. A storm is not hostile to the leaf it tears away. The leaf simply cannot withstand the storm. The storm has no awareness of the leaf. Likewise, the universe has no awareness of life. But life, being aware, interprets these consequences as struggle, as adversity, as harm. In truth, They are merely the unfolding of laws that never pause, never adjust, never differentiate between structure and organism. Yet the most profound part emerges here, in the quiet edges of this realization. The absence of intention does not diminish the difficulty life faces. It deepens it. Fighting an enemy with intention allows strategy. Fighting a system without intention allows no negotiation, no compromise, no appeal. Life must adapt not to motives, but to mechanics. Mechanics do not stop. And so life must constantly rebuild what the universe erodes. It must shelter itself against processes that cannot be slowed. It must repair damage inflicted without malice, simply because the world around it shifts according to fundamental laws. This makes life's persistence not only improbable, but remarkable. It survives in spite of rules that harm it incidentally, repeatedly, and comprehensively. It finds ways to flourish between the blades of a system that never meant to sharpen them. And within that struggle, unintended though it is, life develops the very things the universe does not generate: patience, resilience, memory, perception, meaning, qualities that do not serve the universe's rules, yet serve life's ability to continue despite them. There is a quiet shift that happens after seeing how the laws harm without intending anything. A shift not in the universe, but in ourselves. It begins as a small crack in an old assumption, the assumption that the cosmos is, in some elemental way, connected to us, that it is our backdrop, our origin, our context, our home. But when you look carefully, that feeling begins to dissolve. It wasn't the universe that created that sense of belonging. It was us, projecting familiarity onto a place that has never been familiar, painting intention onto a system that has never held intention, mistaking the narrow pocket we inhabit for the entirety of what is possible. Human beings evolved in an environment so gentle, so rare, so improbably balanced, that it shaped our minds into believing that stability is natural, that safety is normal, that warmth is expected, that continuity is a given. But these ideas are local truths. They are Earth truths. They are not universal. Every feature that made Earth feel like a cradle, the oxygen-rich air, the moderate temperatures, the shielded magnetosphere, the presence of water, the slow seasons, the long stretches between catastrophes, was never the rule. These were coincidences, layered delicately across billions of years. The universe beyond Earth has never resembled a cradle. It resembles something else entirely. Vast, indifferent machinery, moving according to laws that do not notice the fragile forms living within small, sheltered corners. And yet, from the moment consciousness emerged, humans built meaning out of patterns. We looked at the stars and assumed they looked back. We saw cycles and assumed purpose. We traced constellations and assumed guidance. We felt wonder and assumed invitation. The first stories we told were attempts to bring the universe closer, to shrink it into myths and symbols we could hold. We believed storms spoke. We believed comets warned. We believed the sky responded. These beliefs were not foolish. They were adaptive. In a world where survival depended on understanding patterns, the safest assumption was that the world had intentions. Intentions can be predicted. Mechanics cannot. But the universe never changed. Only our models of it did. As astronomy expanded, the familiar sky grew stranger. Stars were revealed as suns, nebulae as nurseries, galaxies as island universes. Distances grew so large that light itself struggled to describe them. And still, the old instinct lingered, to look upward and feel that this vastness somehow included us. But inclusion is not what the universe offers. The universe offers consistency, nothing more. Its stars are not lanterns placed above us. They are nuclear engines burning themselves apart. Its planets are not platforms designed for life. They are debris cooling from older fires. Its rhythms are not messages. They are consequences. The feeling that the cosmos is somehow aligned with our existence is not born from physics. It is born from the architecture of human perception. Perception evolved to find meaning in noise, to detect agency where none exists, to interpret coincidence as design. to build narratives out of neutral patterns. On Earth, this tendency kept us alive. In the universe, it misleads us. When early thinkers imagined celestial spheres, they placed Earth at the center, not because the evidence suggested it, but because the mind craves a position of relevance. When later thinkers discovered heliocentrism, they still believed the solar system was special. When galaxies were identified, we imagined ours was central. When the expansion of the universe was measured, we assumed the expansion treated us gently. Each time, the universe corrected us. Not through hostility, but through indifference. The deeper we look, the more the universe removes us from centrality. We are not in the middle of anything. Not in space. Not in time. Not in the hierarchy of matter. Not in the architecture of forces. Not in the sequence of cosmic events. By every measurable metric, life is not the narrative of the universe. It is a footnote, and yet we continue to read the universe as if it were a story about us, because that is the only scale at which the world feels comprehensible. This mismatch between perception and reality is also visible in our intuitions about stability. We feel as though the world should remain stable, because our psychology was shaped inside a narrow slice of time when Earth happened to be calm. But calmness is not typical. It is borrowed, a temporary state between catastrophes. Earth has been struck by asteroids large enough to reset evolution. Earth has frozen over almost completely. Earth has boiled under runaway greenhouse episodes. Earth has lost oxygen, regained oxygen, lost biodiversity, regained it. We call Earth's present stability normal, when in truth, it is abnormal. We just happen to be living inside the anomaly. And from within that anomaly, our minds formed assumptions. Assumptions about permanence. Assumptions about patterns. Assumptions about safety. These assumptions worked locally, but when projected onto the universe, they distort everything. The universe does not promise continuity. The universe does not promise habitability. The universe does not promise future stability, even for Earth. Stars brighten, orbits drift, magnetic fields collapse, planets cool, vacuum energy pushes galaxies apart, entropy deepens its reach. At every scale, stability is temporary. Continuity is rare. Habitability is fragile. The old belief that the cosmos is home collapses under this understanding, not because the universe is cruel, but because home implies care, intention, preparation. The cosmos offers none of those. What it offers is structure, and life must assemble meaning within that structure, not from it. There is also an emotional layer hidden beneath these shifts in understanding. When we believed the universe was built for us, even loosely, our place in it felt secure. When we saw Earth as the center, life felt destined. When we believed in cosmic purpose, survival felt justified. But once the scaffolding of meaning dissolves, we are left with something colder and more honest. A universe that does not notice we are here and will not notice when we are gone. Yet strangely, this honesty opens a new kind of clarity. A clarity not born from fear, but from seeing ourselves without the distortions of ancient stories. If the universe never meant to host life, then life is not wrong for existing. It is simply unexpected. It is not breaking the rules. It is threading itself through the narrow places where the rules relax. Life becomes not a cosmic intention, but a cosmic improvisation. And improvisation carries a form of beauty that design cannot match. It is spontaneous, unscripted, unbounded by expectation. In this light, the universe's indifference stops feeling like rejection. It becomes a backdrop, silent, vast, unmoved, against which life performs a brief, improbable act of coherence. We are not here because the universe made room. We are here because the universe did not close every door. And in the quiet that follows this realization, you begin to sense that existence does not require belonging. It only requires persistence. Just long enough for awareness to flicker, for memory to take shape, for meaning to arise in minds that evolved on a tiny world, circling an unremarkable star. In a galaxy, the universe will eventually let drift into darkness, unseen, untouched, but momentarily alive. Once you let go of the idea that the universe was meant for us, another truth emerges. One that feels less like a revelation and more like a quiet unveiling. The sense of cosmic isolation that haunts human thought is not an illusion. It is not existential imagination, nor the result of limited communication, nor the product of our smallness alone. It is structural. Loneliness, on the scale of the universe, is not an emotion. It is architecture, woven into spacetime itself. The cosmos is built in a way that prevents connection by default. It separates. It isolates. It distances all things from one another as time passes. Even before dark energy accelerates the universe outward, space-time defines boundaries of reach. Light has a finite speed. Signals have limits. Gravity weakens with distance. Information cannot travel instantly. Every law that governs motion also governs separation. These rules make closeness rare, and rarity gives rise to the strange, persistent solitude that permeates the fabric of existence. The largest structures of the universe, the cosmic web of filaments, clusters, and voids, demonstrate this pattern vividly. Galaxies are not scattered evenly. They are threaded like beads along vast, tenuous strands. Between these strands lie immense voids, regions devoid of stars, planets, energy gradients, or anything life could inhabit. These voids are not anomalies. They are the majority. The typical location in the universe is isolation. The typical environment is emptiness. The typical distance between habitable systems is enormous. Our world sits in one of the rare, dense regions, one cluster within a long filament within a larger web. But even among these clusters, the separation is immense. The nearest star is 4 light-years away. The nearest habitable candidate, farther still. The nearest galaxy is 2.5 million light-years away. This is loneliness expressed in units of time, not feeling. And beyond physical distance, there is causal distance, one of the most profound forms of separation in physics. Because light travels at a finite speed, not all regions of the universe can influence one another. The farther apart two places are, the less they share a common history, a common fate, a common exchange of information. The horizon of what we can ever see, ever know, ever reach shrinks as the universe expands. More galaxies move beyond it each moment, not because they move faster, but because space-time itself stretches between us. In the far future, almost everything will disappear beyond causal reach. The night sky will empty, the cosmic background will fade. The universe will become a set of isolated islands, drifting alone through a darkening sea. This loneliness is not temporary. It is intrinsic. Yet, even now, before the distant future arrives, the universe already expresses this isolation in quieter ways. Consider the light from distant galaxies. What we see is not what they are, but what they were millions or billions of years ago. We never witness them as they exist now. Communication is one way, delayed, incomplete. Even the information that reaches us is diminished by expansion, distorted by redshift, stretched until its structure dissolves into faint microwaves. Everything distant is also ancient. The universe does not allow simultaneous experience across vast separations. To know something far away is to know a ghost of its past. This temporal loneliness is embedded in the equations of relativity. Time is not universal. It flows differently for different observers. No two clocks, separated by distance or gravity, truly agree. Shared experience, the foundation of connection, breaks down on cosmic scales. Even our galaxy is bounded by isolation. The Milky Way is one of a few dozen major galaxies in a small local group. Beyond that group lies the Virgo supercluster, and beyond that, Laniakea, a still larger structure. But even these vast cosmic families are temporary. Dark energy will eventually pull them apart, breaking even the concept of cluster. Bonded structures will become solitary artifacts scattered through expanding spacetime. And at every scale, the trend is identical. The universe builds temporary collections, then lets them drift apart. This pattern recurs at the scale of stars. Stars form in clusters, thousands of siblings igniting from the same cloud. But as the cluster evolves, gravitational nudges fling stars outward. The siblings scatter across the galaxy. The memory of their shared birth dissolves into distance. Stars are born together. They die alone. Planets, too, form from shared disks of dust and gas, but their orbits gradually diverge. Worlds rarely remain in resonances for long. Gravity perturbs. Collisions eject. Tidal forces drift. In time, no two planets remain close companions. Even at the scale of matter, loneliness persists. Atoms bond and break. Molecules assemble and disassemble. Particles interact briefly, and then separate forever. Quantum entanglement creates correlations, but not enduring contact. Its connection is mathematical, not spatial. Nothing remains attached long. Nothing remains connected without cost. This structure of separation carries into biological scales as well. Organisms grow from shared origins, yet diverge constantly. Cells replicate but drift genetically. Populations split. Species branch. Lineages fork. Each path moves away from its siblings. Life mirrors the cosmos. Expansion followed by isolation. Even consciousness reflects this architecture. Every mind is an island. Thoughts arise alone. Perception is private. Experience is incommunicable in its pure form. We spend our lives trying to bridge these internal distances with language, empathy, memory, yet the separation between minds never fully closes. The loneliness inside us is not psychological, it is cosmological. It is the interior echo of a universe built on distance, drift, and isolation. Human beings sensed this long before science articulated it. Ancient myths spoke of separation between heaven and earth, between gods and mortals, between fate and choice. Philosophers wrote about the solitude of being conscious in a world that does not answer back. These intuitions were not mistakes. They were reflections. Even early stargazers felt the vastness above them as something unreachable, not because they lacked technology, but because they sensed, in some deep, intuitive way, the inherent separation knitted into the universe. The cosmos does not provide closeness. Closeness must be created, locally, briefly, precariously. Life is the only process we know that generates connection rather than distance. Organisms bond. They communicate. They cooperate. They reproduce. They build continuity and memory. They form networks that mirror cosmic webs, but with the opposite purpose, not to isolate, but to bridge. Where the universe expands outward, life gathers inward. Where spacetime creates voids, biology creates communities. Where physics spreads, evolution concentrates. The two processes move in opposing directions, but life cannot erase the architecture it finds itself in. It can only work within its boundaries, creating temporary constellations of meaning before drift resumes. Still, understanding loneliness as a structural feature of reality does not make life smaller. It makes life sharper, more defined, more improbable, more aware. Isolation is the universe's default, but connection is life's creation. And every connection, every shared moment, every thought, every fragile thread stretched between beings becomes a quiet act of resistance against a space-time built for solitude. Not because we can escape the loneliness of the universe, but because we can briefly, beautifully interrupt it. Once you recognize that loneliness is written into space-time itself, that separation is not an accident, but a fundamental property of the cosmos, another realization unfolds almost reluctantly. It is not only space that drifts apart. It is not only galaxies that slip beyond reach. It is not only living things that fade with time. Matter itself grows tired, not in the human sense, not with emotions, but with a subtle, inevitable unraveling built into the deepest structure of particles. Everything that exists, atoms, stars, planets, cells, carries an expiration date encoded in the physics of its constituents. The universe does not merely isolate, it erodes. And the erosion begins at scales far smaller than planets or stars. It begins with the building blocks of reality. Protons, long considered eternal, are now suspected to decay over extraordinary timescales. If this is true, then nothing made of ordinary matter is permanent. Not atoms, not molecules, not the chemical scaffolding of life, not even the stars themselves. Proton decay, if it occurs, happens so slowly that entire civilizations rise and die. Galaxies collide and separate. Black holes form and evaporate, all within the prologue of its timeline. But however slow, the direction is unmistakable. Matter drifts toward simplicity. The universe is not only expanding, it is emptying. Even if protons do not decay, quantum instability persists. Particle interactions depend on fields that fluctuate. Vacuum states can shift. Decay pathways open under new conditions. Entropy pulls relentlessly on every structure. Matter holds itself together only temporarily. In the early universe, particles were young, fresh, energetic, structured by symmetry-breaking events that gave rise to forces and masses. But as time passes, the energy that once animated matter dissipates. Thermal motion slows. Chemical reactions stall. Nuclear processes weaken. The universe cools not only in temperature, but in potential. Stars have long been the symbols of endurance, yet even they grow tired. Massive stars burn too quickly. Small stars burn too faintly. Medium stars like the Sun last only a fraction of cosmic time. Fusion is not sustainable. It is consuming. A star shines by destroying mass and converting it to energy. Eventually, the fuel runs out, and the star collapses, or expands, or cools into a fading ember. Every star is a clock. Every element forged in its core is a residue of its exhaustion. But the exhaustion does not end with stars. White dwarfs cool until they become black dwarfs, frozen remnants, radiating nothing. Neutron stars will eventually lose rotational energy, their magnetic fields collapsing into quiet, inert spheres. Black holes evaporate through Hawking radiation, losing mass until they vanish completely. The universe is a sequence of diminishing returns, and matter follows the same downward arc. On human scales, matter feels solid, stable, reliable. The chair supports. The ground holds. The body persists. But stability is an illusion of short timescales, an illusion created by our brief lifetimes compared to the long arc of cosmic evolution. If you could watch matter on the scale of trillions of years, you would see it behave differently. You would see atoms losing energy. You would see particles drifting toward decay. You would see molecules failing to bond as temperatures approach absolute zero. You would see structure dissolving into emptiness. Matter does not decay explosively. It decays quietly. This quietness is what makes its exhaustion so profound. Nothing announces the beginning of matter's senescence. There is no cosmic signal, no transition, no event. The slow fading begins the moment matter forms and continues forever. Even now, in a universe still young by its own standards, the signs are visible. Stars are fewer than they once were. Gas clouds are thinner. Galaxies no longer form as frequently. Interstellar space grows colder. Dark energy accelerates expansion, reducing the density of matter further. The cosmic environment that once encouraged structure is gradually withdrawing its support. Life depends on complexity, but complexity requires matter that is energetic enough, stable enough, mutable enough to form bonds, reactions, and feedback loops. As the universe ages, those conditions deteriorate. Chemical energy becomes scarce. Temperature gradients flatten. Heavy elements become trapped in remnant stars. Radiation becomes too diffuse to drive meaningful reactions. Molecular motion slows until chemistry itself goes dormant. The exhaustion of matter is the exhaustion of life's potential. Even before proton decay becomes relevant, matter loses its utility for biology. In a cold, diffuse universe, molecules cannot self-assemble. Reactions cannot overcome activation barriers. Membranes cannot maintain structure. Enzymes cannot operate. Metabolism cannot proceed. Life requires matter in its active phase. The universe offers that phase only briefly. This realization changes the way we perceive existence. We tend to think of matter as the most solid foundation, unchanging, dependable, the one part of reality immune to the passage of time. But matter is not immune. Matter ages. It ages through decay, through cooling, through cosmic expansion, through nuclear instability, through entropy. We live in an era of matter that can still form stars, still form planets, still form organisms capable of reflection. But this era is temporary. It is not the default state of the universe. It is the product of a narrow window between the violent beginnings and the quiet endings of matter. A window where energy gradients still exist, where temperature differences still drive reactions, where atoms still bond with enough vigor to form complexity. The early universe was too hot. The distant future will be too cold. We live in the brief middle period where matter has cooled enough to allow structure, but not so much that structure freezes in place. The exhaustion has not yet overtaken everything, but the trend is clear. Matter tends toward dormancy. Particles tend toward decay. The universe tends toward stillness. This stillness is not peace. It is absence. Absence of reaction. Absence of formation. Absence of energy. Absence of life. And when you see matter through this lens, not as the eternal canvas of existence, but as a temporary scaffolding, you begin to understand the fragility of everything built upon it. Life depends on matter the way a fire depends on oxygen. As matter exhausts, the flame dims. The atoms in your body were forged in stars billions of years ago. Those stars burn themselves to death to create you. The calcium in your bones carries the imprint of a star's exhaustion. The iron in your blood was born in a supernova's collapse. The carbon in your cells once drifted as smoke through a dying giant's atmosphere. Your existence is threaded into the fatigue of matter. Life is not separate from cosmic exhaustion. It is one expression of it. Even consciousness, the most delicate form of matter's self-organization, depends on atoms that hold their structure only temporarily. When the atoms eventually decay, the patterns they sustain will dissolve. Nothing persists, not because the universe destroys, but because matter cannot sustain. This does not diminish the value of existence. It deepens it, because all living things arise not from abundance, but from scarcity, not from permanence, but from transition, not from stability, but from the brief interval where matter is energetic enough to assemble form and stable enough to hold it. We live inside that interval, an interval carved from the exhaustion of stars, sustained by the temporary coherence of atomic forces, illuminated by a universe that is slowly dimming. Matter is growing tired. But in its tiredness, it shapes beings capable of noticing, beings capable of understanding that existence is not about lasting, but about emerging, briefly, delicately, before returning to the quiet toward which all matter drifts. Not a fall, not a failure, but the natural arc of everything that has ever been built, from particles trying to hold themselves together in a universe that gradually asks them to let go. Once you understand that matter itself grows tired, that its endurance is temporary, that its structures loosen over unimaginable spans of time, another realization drifts quietly into view. The universe is heading toward a state where even the possibility of life evaporates. Not in a sudden catastrophe, not in a violent ending, but in a long, slow diminishing, like a flame shrinking as its fuel thins. Life ends not because something attacks it, but because the universe gently removes every condition that once allowed it. This fading begins on scales too vast for any species to notice in real time. Yet, the trajectory is unmistakable. Stars die one by one. Their heat dissipates. Their remnants cool. Their light spreads thin across expanding space. The matter they leave behind becomes increasingly inert. And all the while, dark energy continues its soft, persistent work, pulling galaxies away from one another, thinning out the universe until emptiness itself becomes the dominant landscape. Life needs density. The universe moves toward dilution. Life needs gradients. The universe moves toward equilibrium. Life needs energy. The universe moves toward exhaustion. The story of the far future begins with the cooling of stars. Most stars today are young by cosmic standards. They burn brightly, creating regions of warmth where life can form. But stars are temporary structures. When they exhaust their hydrogen, they expand, transform, collapse, or explode. In every case, the stable period ends. Massive stars die quickly. Medium stars swell into red giants, then collapse into white dwarfs. Small stars burn for trillions of years, but they do not burn forever. As time moves on, the universe fills with remnants, white dwarfs fading into black dwarfs, neutron stars spinning down into dark spheres, black holes evaporating slowly through Hawking radiation. The cosmos that once shone with billions of brilliant points becomes a graveyard of cooling embers. At first, life may still find places to endure. Around stable red dwarfs, around the last warm worlds, inside artificial habitats built by civilizations persistent enough to outlive stars. But the options shrink as the universe cools. In the era that follows, matter itself changes behavior. Atoms remain stable, but chemical reactions slow as temperatures drop. Molecules struggle to find energy sources. Thermal noise, once the driver of the chemical randomness life exploits, falls toward zero. Without warmth, chemistry stops. Without chemistry, metabolism stops. Without metabolism, life stops. Cold is not merely the absence of heat. It is the absence of possibility. The universe becomes a place where reactions cannot proceed, where gradients flatten into stillness, where the spark of self-sustaining complexity disappears, not because it is extinguished, but because there is no longer anything for it to grasp. Life dies not by destruction, but by starvation. On even longer timescales, gravity reshapes the universe once more. Stars vanish, but black holes remain. Galaxies no longer shine, but their dark centers continue to warp spacetime. Planets drift cold and silent. Free-floating worlds wander through endless night. Civilizations, if any survive long enough, must confront a future in which usable energy becomes scarce. Fusion is gone. Starlight is gone. Heat sources become weak whispers in a dark so complete that distance ceases to hold meaning. At this stage, survival becomes almost theoretical. Only the cleverest manipulations of matter and energy could postpone the end. Only structures built around the last particles of heat could persist. But even these efforts face a boundary: the heat death of the universe. Heat death is not a dramatic event. It is the moment when temperature differences disappear, when everything reaches the same low, silent equilibrium. Energy no longer flows. Work can no longer be done. Structures can no longer maintain themselves. Life is a pattern built on asymmetry, on imbalance, on gradients. When the gradients fade, the pattern flickers out. Even information, which once seemed eternal, becomes fragile in this landscape. Memory requires physical stability. Computation requires energy. Storage requires coherence. All of these depend on matter that can resist entropy, matter that can hold form against time. In the far future, even form dissolves. Black holes evaporate. Protons may decay. Neutrons break apart. Atoms vanish. The particles that remain drift apart in expanding space until interactions become impossibly rare. The universe becomes transparent to its own emptiness. And yet, even in such a distant, cold, nearly quiet scenario, the fading is not a failure. It is simply the natural trajectory of a cosmos governed by laws that favor equilibrium. Equilibrium is stillness. Stillness is death for life, but not for the universe. The universe continues, not alive, not dead, but simply existing in its final, most uniform state. The eerie part is not the end itself, but how gently it arrives. No explosion, no collapse, no dramatic finale. Just a slow thinning of possibility until complexity becomes impossible. This fate reframes our understanding of life's place in cosmic history. Life is not a permanent feature, nor a widespread one, nor even a durable one. It is a spark caught between two vast eras of noise and quiet, the fiery chaos of the beginning and the silent stillness of the end. Between those extremes, life emerges, thrives for a moment, reflects on its own existence, and then fades. But in that moment, however brief it may be, the universe becomes aware of itself through living eyes. Matter learns to question. Energy learns to think. A temporary condensation of atoms forms a mind capable of understanding that both the beginning and the end are indifferent. There is a strange dignity in that, a quiet defiance, a beauty that emerges not from permanence, but from ephemerality. For the universe, the end of life is simply the resumption of silence, a return to the baseline state of existence, a settling of the cosmic dust, But for life, for beings capable of noticing the fade carries weight. Not because it is avoidable, but because it is meaningful. Meaning does not survive the universe. Meaning survives within it. And in recognizing the fading of everything, life discovers the depth of what it means to exist at all. To shine for a moment in a cosmos that will one day forget every atom that ever composed a living thing, yet was briefly illuminated by their warmth. As the universe drifts toward its quiet future, toward thinning starlight, cooling remnants, dissolving matter, another realization begins to unfold, not from physics, but from the strange interior landscape of consciousness itself. If everything is fading, if the cosmos grows colder with time, if matter unravels, if life persists only briefly, in a universe that never meant for it to exist, then why does the briefness feel significant? Why does a passing flare of complexity carry weight? In a reality built from forces that never pause to notice it? It is because significance does not originate in the universe. It originates in life. In the margins of an indifferent cosmos, meaning emerges not from what the universe provides, but from what life chooses to make of its improbable moment. This insight rises slowly, like dawn after a long night. It begins with the recognition that rarity is not emptiness. Rarity is value. Everything scarce in nature becomes precious. A stable world, a warm star, a quiet century, a moment of consciousness. The more improbable something is, the more it stands out against the backdrop of everything that is not. Life is a statistical accident, but that accident carries the unique property of being able to reflect on itself. It can observe the very universe that does not intend for it to exist. It can look outward into silence and generate understanding, questions, patterns, all things that physics alone cannot produce. From this perspective, life is not at odds with the cosmos. It is the part of the cosmos that resists equilibrium long enough to think, and thought itself becomes a kind of illumination. The fading of the universe does not diminish intelligence. It sharpens it. It transforms awareness into something fragile and luminous. Something that exists only because the universe, by coincidence, failed to prevent it. Complexity is more meaningful when surrounded by vast simplicity. Awareness becomes profound when surrounded by unawareness. Connection becomes profound when surrounded by cosmic solitude. The value of life is not reduced by the universe's indifference. It is defined by it. The very fact that the universe doesn't try to create or protect life means that every instance of life reflects an extraordinary alignment of circumstances. A moment where physics, chemistry, geology, and time all relax their constraints, not intentionally, but enough for awareness to slip through. Meaning is the name life gives to this improbable passage. Consider intelligence not as an inevitable endpoint, but as a rare visitor that appears only where conditions remain stable long enough for minds to evolve. A mind is the result of countless accidents, mutations that didn't fail, ecosystems that didn't collapse, climates that didn't destabilize. A mind is matter temporarily arranged into something that can feel wonder, feel fear, feel longing. Matter itself does not long for anything, but once arranged into a mind, it does. The universe does not ask questions, but once arranged into a brain, it asks. The universe does not feel lonely, but once arranged into a human, it aches. Loneliness, longing, meaning. These are not cosmic properties. They are biological responses to a cosmos that offers no guidance, no comfort, no narrative. And yet, by arising within that cosmos, they give it something it cannot generate alone: perspective. A star does not know it shines, but an organism can watch it shine and turn that observation into meaning. A galaxy does not know it spins, but a mind can trace its arms and sense the elegance of its motion. A universe does not know it exists, but a consciousness can exist within it and whisper the fact that it does. This is the quiet paradox of existence. Life is insignificant to the universe, yet infinitely significant to itself. The universe provides no purpose, yet life builds purpose out of its own persistence, and in that construction lies something extraordinary. Purpose is not given, it is created. It grows from the fragile chemistry of neurons and experience. It emerges wherever life chooses to interpret survival as something more than repetition. Meaning is a choice that matter makes. Once matter becomes alive, once matter becomes aware, it is easy to imagine that meaning should come from outside, from cosmic intention, from destiny, from design. But meaning is more honest, more resilient, more profound when it arises from within. A universe without intention gives life freedom. Freedom to define itself. Freedom to decide what matters. Freedom to care. The universe does not care, but life does. And that difference changes everything. For countless ages, the cosmos expands, cools, darkens. Stars fade. Matter thins. Time stretches. But within that immensity, life briefly concentrates order. It pulls scattered atoms together and teaches them to think. It transforms random chemistry into memories, emotions, questions. Life becomes the universe noticing itself. Even if no other intelligence exists, even if humanity is alone, even if our world is the lone oasis in a desert older than imagination, awareness is still real. Meaning is still real. The rarity does not weaken it. It strengthens it. A single candle in an endless night is more striking than 1,000 candles in a lit room. Life is that candle. The universe's indifference does not extinguish it. It makes its flame sharper, brighter, more improbable. And through that improbability, life finds a truth. The cosmos never speaks aloud, but silently displays. Meaning is not found in the universe, but in the fact that the universe allowed something rare enough to wonder what it means. If meaning arises only because life chooses to create it, if significance exists only in the narrow places where consciousness blooms, then there is something even more delicate waiting beneath these realizations. Something that sits at the very center of why life matters in a universe that never asked for it. Life holds a quality the universe does not: awareness. Not awareness as a property of stars or planets or galaxies, but awareness as something that exists only in the small, warm pockets where matter arranges itself into minds. The universe expands, but it does not observe. It acts, but it does not reflect. It unfolds, but it does not remember. Life does all three. Life notices. Life stores. Life questions. In doing so, it adds an ingredient to reality that the universe would not possess without it. The ability not only to be, but to know that it is. Awareness is the thin thread that transforms existence into experience. And experience is something the cosmos cannot generate on its own. When a life looks at the stars, something unprecedented happens. The universe becomes visible to itself, not objectively, for no perspective can capture the whole, but locally, intimately, through the eyes of a single organism, on a single world, orbiting a single star. That act of seeing, of noticing, of wondering, of asking, is the first time in cosmic history that the vast machinery acquires a point of view. It is a small miracle, not because it changes the universe, but because it changes the experience of it. The universe remains indifferent, but the moment something living stares into its darkness, darkness becomes a backdrop, not a void. Even questions, the simplest product of awareness, reshape the atmosphere around existence. A question bends meaning into the places where physics alone is silent. A question allows life to explore not just what is, but what is possible, what could be, what should be. Questions are how life pushes against the boundaries of ignorance, how it expands experience even when the universe itself is contracting the opportunities for survival. The fact that life wants to understand is not trivial. It is the rarest impulse in the cosmos. Stars do not inquire. Atoms do not wonder. Galaxies do not doubt. But a single mind, quietly awake on a spinning sphere of rock, can hold more curiosity than an entire galaxy can generate in its billions of years of motion. This is the quiet gift life brings into existence. A gift the universe did not anticipate, did not request, but nonetheless receives through the brief presence of minds. Awareness is not immune to the universe's fading, though. As stars dim, and matter cools, and galaxies drift apart, the environments capable of supporting minds shrink. Eventually, the last worlds warm enough for consciousness will go silent. The last biological networks will dissolve. Even artificial minds, should they exist, will require energy that can no longer be extracted from a universe tending toward equilibrium. When awareness finally ends, the universe will return to a state where nothing sees it, nothing asks, nothing wonders. Yet the presence of awareness, even temporarily, changes the story not for the universe, but for itself. Meaning does not need to last to matter. An echo is still an echo even if it fades, and life's echo is long. It reverberates through memory, culture, communication, art, scientific understanding. It ripples through time as long as minds survive to carry it. Even when those minds are gone, their existence remains a fact woven into the universe's history, a chapter that cannot be unwritten, even if no one remains to read it. Physics records everything, not deliberately, but unavoidably. Information imprints itself into the evolution of matter. Every living moment changes the configuration of particles in tiny, irreversible ways. Awareness leaves fingerprints, and those fingerprints linger, embedded in the cosmic fabric, subtle but real, marking the brief era when atoms learned to arrange themselves into eyes that opened. There is a strange beauty in the idea that awareness is temporary but not pointless. The universe does not remember us, but the patterns we created existed, and that existence alone is enough. It is enough that life noticed. It is enough that life wondered. It is enough that life cared. We measure significance not by duration, but by depth. Even if the universe forgets, life does not. Life creates significance inside moments that physics would otherwise leave untouched. The significance begins and ends within life itself, and that is enough. Because the act of perceiving transforms existence into meaning, even if only locally, even if only briefly. In this way, life is not opposed to the universe. It is the universe expressed in a form that can reflect, feel, and hold thought like a flame cupped between trembling hands. Awareness is the universe waking up, for a moment, to see itself before it sleeps again. And in that moment, that small, fragile, extraordinary moment, everything becomes illuminated with a kind of softness the universe itself does not produce. A softness born not from stars, but from minds, a warmth born not from fusion, but from meaning, a light born not from photons, but from understanding. Close your eyes now. The universe continues its slow turning, and for a moment longer, you are here to witness it.